In 2012, we didn't just find a new particle, we proved that empty space isn't empty. It has a hidden structure, a field with a precise symmetry, and it quietly decides which particles are allowed to have mass at all. So what is the Higgs boson, mathematically and physically, and how can a background field give mass without breaking the standard model's gauge symmetry? One number, one vacuum value, rearranges the electroweak world, and the universe never looks the same again. Follow the equations far enough, and mass stops being a label, becoming a consequence of how the theory is allowed to exist. To understand the Higgs, we have to be stricter than popular explanations allow, and more literal than intuition prefers. This story begins where physics always begins, with fields as functions on spacetime, and with dynamics written as an action. From there, particle becomes a precise statement about quantized excitations, and mass becomes a pole in a propagator. The difficulty is not technical decoration, it is the central obstacle the standard model had to clear. A gauge theory of spin-one fields can be consistent only if its symmetry is treated as a real constraint, not a stylistic choice. Write the wrong term into the Lagrangian, and at high energy the theory announces its failure, through amplitudes that grow too fast, through lost unitarity, through predictions that cannot be completed. And yet the weak interaction is unmistakably short range, which means its carriers are heavy. The puzzle is sharp. The same electroweak symmetry that organizes the interactions forbids the mass terms the data seem to demand. Any serious answer must show, step by step, how the symmetry remains exact in the equations, while the spectrum of particles changes anyway. That answer will not be delivered with metaphors, only with definitions, transformations, and the minimal mathematics that makes those words mean something. We will build the Higgs sector from the ground up, not as a story about a special particle, but as a particular scalar field with a particular representation. We will watch how a potential selects a vacuum, and why a vacuum can carry structure without contradicting Lorentz invariance. We will see what it means for symmetry to be spontaneously broken, and why that phrase hides a careful distinction between the Lagrangian and the state. Then the real test arrives, local symmetry, where the degrees of freedom must balance, and where the would-be massless modes cannot simply be left behind. By the time we return to the 125 GeV resonance, it will appear in its proper place within the theory, an excitation around a vacuum configuration, with couplings fixed by gauge invariance and by the value of V. Its decays and production channels will matter, but mainly as measurements of structure, not as a catalogue of signatures. And when we finally step outward to the early universe, the same field will become an evolving order parameter, sensitive to temperature and to the history of the vacuum itself. Because once a vacuum has a value, a deeper question follows. Why that value? Why that potential? And why this particular electroweak world rather than another? Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Across 7 chapters, we move from the LHC signal to the field theory that makes it interpretable, then to the gauge invariant mechanism that reshapes the spectrum. And at the end, we take the Higgs back into cosmic time, where its vacuum becomes a historical event with unfinished implications. In July 2012, 2 detectors at CERN reported a new resonance near 125 giga electron volts. The signal appeared in multiple decay channels, and it rose above backgrounds that had been modelled with obsessive care. The announcement was careful, almost restrained. This was a particle consistent with the Higgs boson, not a final proof of every Higgs idea. What was discovered was a narrow bump in invariant mass distributions, reconstructed from sprays of particles and bursts of light in dense detector layers. In the plots, the excess was small but persistent, sitting where random fluctuations were unlikely to gather twice. It behaved like a new quantum field excitation produced in high-energy proton collisions, emerging from gluon fusion and other production modes. Its measured mass settled near 125 GeV, with uncertainties that shrank as data accumulated and calibrations improved. Its observed couplings scaled with particle masses in the pattern the standard model predicts, within experimental precision and within the limits of early statistics. The cleanest channels were rare, and that rarity was part of the story. 2 photons, for example, made a sharp mass peak because the electromagnetic calorimeters measured energies with high resolution. 4 leptons from 2 Z bosons gave an even cleaner signature. 4 isolated tracks, 4 measured momenta, and a reconstructed mass that looked almost too neat. Other channels, like decays to bottom quarks, were swamped by ordinary strong interaction events, so the signal had to be extracted with multivariate methods and careful control regions. Spin and parity were tested through angular correlations and decay products, because a particle's quantum numbers leave geometric fingerprints. The data favoured a scalar assignment, compatible with JP/0+, and the preference strengthened as more events accumulated. That result excluded many alternatives, including most spin-1 possibilities, because of selection rules and observed decay modes. A state decaying to 2 photons cannot be a simple on-shell spin-1 particle, and that fact alone removed a large class of imposters. Still, 0 to plus alone does not prove the entire mechanism that gives masses to other particles, and it does not guarantee the Higgs sector is minimal. A resonance is not a mechanism. A particle is not a background. The Higgs boson is the quantum of a field, while the field's vacuum value is the persistent ingredient that shapes everything else. This chapter starts with that distinction, because the title is literal and the confusion is common. The particle was not the point, even though it was the headline. We set rules now because precision is the only way to keep the mystery honest. No analogies, no metaphors, and no comforting pictures that hide the mathematics. We use definitions, equations, and physical consequences stated as directly as possible. When we say field, we mean a function of space-time that can be quantized, with operators that create and annihilate excitations. When we say mass, we mean a parameter in the equations of motion that controls dispersion and rest energy, and that appears as a pole in a propagator. A field assigns values to every point in space-time, and in relativistic theories it must transform properly under Lorentz transformations. In quantum field theory, excitations of a field appear as particles with specific quantum numbers, including spin, charge, and gauge representation. A Lagrangian density encodes the dynamics, including kinetic terms, interaction terms, and potential terms that determine the vacuum structure. The action S is the space-time integral of the Lagrangian, and stationary action gives the field equations through the Euler-Lagrange formalism. That compact principle is why modern particle physics can be written on a page, even when its consequences fill libraries. Symmetries are transformations that leave the action invariant, and they are not aesthetic extras. Continuous symmetries imply conserved currents through Noether's theorem, linking abstract invariants to measurable conservation laws. Local symmetries require gauge fields, because the theory must compensate for transformations that vary from point to point. The vacuum state is the lowest energy state consistent with the theory's constraints, including gauge structure and boundary conditions. A vacuum expectation value is the expectation of a field operator in that vacuum, written 0 Pirsterost, and it is a number that can quietly reshape the spectrum. The Higgs field in the standard model is a complex SU2, L doublet, usually written F, and it carries hypercharge under U1Y. Its potential is chosen so that the lowest energy configuration has non-zero magnitude, which is a statement about the sign of the quadratic term and the stability of the quartic term. The vacuum expectation value V is defined by phi0, with V 246 GeV, and that number is fixed by measured weak interaction strength. The Higgs boson is the fluctuation around that vacuum configuration, one physical scalar degree of freedom after gauge choices remove redundant components. The other degrees of freedom do not vanish. They are reorganized into the longitudinal polarizations of massive gauge bosons. The discovery at CERN was evidence for that fluctuation mode, seen as a resonance with a definite mass and measurable decay patterns. It was not a direct measurement of V as a background, because V is inferred through relations among measured quantities like the Fermi constant and gauge couplings. It was not a direct measurement of the full potential shape, because only limited combinations of self-couplings are accessible with current energies and luminosities. It was not a proof that no additional scalars exist, because new states could be heavier, more weakly coupled, or mixed with the observed state. Even the observed Higgs could be slightly non-standard while still looking standard model, like within uncertainties. The central question of this film is precise, and it is narrower than the headline suggested. What is the Higgs boson in mathematics and in physics, and what does it certify about the underlying field? How can a non-zero Higgs vacuum expectation value generate particle masses without breaking the gauge symmetry that defines the standard model? If the symmetry is exact in the equations, why do the particles behave as if the symmetry is hidden? To see the tension, we need the basic structure of the electroweak theory, which was assembled over decades and tested piece by piece. The gauge group is SU2, LXU1, Y, and the structure is not optional because it matches observed charged and neutral currents. Gauge fields correspond to these symmetries, and their interactions are fixed by the requirement of local invariance, including self-interactions for the non-abelian SU2L fields. Fermions come in chiral representations, with left-handed doublets and right-handed singlets, and that chirality is visible in weak decays. The theory is built so that only left-handed fermions feel the full SU2L force, while right-handed fermions do not. Mass terms look simple in classical mechanics, but in a gauge theory they are constrained by representation theory and by renormalizability. A mass term for a gauge boson would be of the form 1.2 m2 aoijun mam, and it is immediately suspicious. That term is not gauge invariant for non-abelian gauge fields, and it breaks the local symmetry that makes the theory consistent and renormalizable at high energies. A mass term for a chiral fermion would couple left and right components, m says l per plans HC, but those components transform differently under SU to LXU1, Y. Writing such a term by hand would violate the very symmetry that correctly predicts how weak interactions treat chirality. So the standard model, written with exact gauge invariance and chiral fermions, seems to forbid explicit masses, and that is the puzzle in its sharpest form. Yet the W and Z bosons are heavy, with masses around 80 and 91 GeV, and their short range is measured in the structure of weak processes. The photon is massless, and electromagnetism remains long range, which is a crucial boundary condition for chemistry and for stars. Quarks and charged leptons have non-zero masses, spanning orders of magnitude from the electron to the top quark. Neutrinos have tiny masses, which already hint that the minimal picture may be incomplete, even if the Higgs framework remains central. This is not a philosophical problem, and it is not a matter of taste in model building. Without a consistent way to generate masses, the electroweak theory fails to match observed weak interaction ranges, scattering amplitudes, and decay rates. The measured Fermi constant, the W and Z masses, and the pattern of neutral and charged currents all point to a specific structure. At high energies, scattering of longitudinally polarized W bosons would grow too large without a mechanism to tame it, and the theory would lose predictive control. The Higgs field background is the simplest structure that preserves gauge invariance while changing the spectrum, and it also restores unitarity in key processes. The key idea is that gauge symmetry can be exact in the Lagrangian while the vacuum is not invariant under the full symmetry. That is spontaneous symmetry breaking, defined without metaphor and without hand-waving. The equations respect the symmetry, but the lowest energy state selects a direction in field space, and that choice is physical because excitations are defined relative to the vacuum. Physical excitations then reorganize into massive and massless modes, with gauge fields absorbing would-be Goldstone degrees of freedom. The symmetry is not destroyed. It is realized in a less obvious way, and the bookkeeping changes. We will build this carefully later, but the outline matters now because it tells you where the masses hide. The Higgs potential is chosen so that the minimum occurs at Fs store. Vos 2, not at Fs0, and that statement is about energy minimization. Expanding the Lagrangian around that vacuum produces quadratic terms that look like masses, because the vacuum value acts like a constant background in interaction terms. For gauge bosons, the covariant derivative term d generates mass terms for W and Z after replacing F by its vacuum value plus fluctuations. The photon remains massless because a particular combination of SU2, L and U1, Y generators leaves the vacuum invariant, defining the unbroken U1. M. For fermions, Yukawa couplings FL, FR plus EHC become mass terms MF F between 2, and the proportionality is exact at tree level. The Yukawa constants are not predicted by the standard model, but once measured they determine both fermion masses and Higgs interaction strengths. That is why the Higgs decays more often to heavy particles when phase space allows, and why the top quark, though too heavy for Higgs decay, dominates key loop processes. In this framework, mass is not a separate ingredient sprinkled onto particles. It is a consequence of how strongly each fermion couples to the Higgs field. Notice what is and is not happening, because the language can mislead even careful listeners. Gauge invariance is not explicitly broken in the Lagrangian, and the theory remains a gauge theory in the strict sense. The vacuum is structured, and the particle spectrum reflects that structure, including the appearance of longitudinal polarizations that behave like the absorbed Goldstone modes. The Higgs boson is the remaining physical scalar excitation, with couplings determined by the same parameters that set masses. This is why measuring its couplings is not an optional detail, and why experimentalists chase percent-level deviations with stubborn patience. It is a test of whether the background field really controls the mass pattern, or whether something else is quietly sharing the job. The 2012 discovery mattered because it completed a missing piece of this structure, and it did so in the only way quantum field theory allows. Before then, we had precise measurements implying V, and we had indirect constraints on the Higgs mass from radiative corrections in electroweak observables. Experiments at LEP and the Tevatron had narrowed the allowed window, and global fits had pointed toward a relatively light Higgs. But we did not have the field's quantum excitation observed as a particle, and without it, the mechanism was an elegant promise without its signature. Finding a scalar resonance with the right properties made the electroweak theory internally consistent in the way it had promised, and it turned a parameter into an object. Yet the discovery also opened new questions, because the Higgs is not just another particle added to a list. The Higgs mass of 125 GeV implies a specific Higgs self-coupling at the electroweak scale, linked to the curvature of the potential around the vacuum. Running that coupling to high energies suggests the standard model vacuum may be metastable, depending on the top quark mass and higher order effects. Metastable does not mean doomed tomorrow. It means the present vacuum could be a long-lived local minimum, separated by an energy barrier from a deeper state. The Higgs sector could be minimal, or it could be the visible part of a larger scalar landscape that only reveals itself through subtle deviations. Now we widen the stakes beyond colliders. The Higgs vacuum expectation value is not just a parameter in a lab, and it is not confined to the ring of the Large Hadron Collider. It is a property of the universe's vacuum state, and the universe has a temperature history written into the cosmic microwave background and primordial abundances. At high temperature, effective potentials change, because thermal fluctuations add corrections to the energy density of field configurations. Symmetries that are broken at low temperature can be restored at high temperature, not by choice but by statistical mechanics. In the early universe, during the electroweak epoch, thermal corrections to the Higgs potential favoured first east 0, because the symmetric phase can be energetically preferred in a hot plasma. As the universe expanded and cooled, the effective potential evolved, and the vacuum shifted to a state with of 0, selecting a direction in field space. That transition is when W and Z masses turned on, and when fermion masses emerged through Yukawa couplings, changing reaction thresholds and decay kinematics. Mass, in this framework, is not a timeless label stamped onto particles at birth. It is a consequence of which vacuum the universe occupies, and that occupancy changed as the cosmos cooled. This matters for cosmology, because changing masses changes reaction rates, equilibrium conditions, and the behaviour of phase transitions. It matters for baryogenesis scenarios that require out-of-equilibrium dynamics and CP violation, because the strength and nature of the electroweak transition can affect whether a symmetries survive. It matters for relic abundances, and for how we interpret early universe constraints on new physics, because thermal histories depend on which particles were heavy or light at which times. Even if the standard model electroweak transition is a crossover rather than a strong first-order transition, the Higgs background still sets the scale of electroweak phenomena. The question lingers in the background: what else might have coupled to the Higgs field in that era, and what traces would that leave? So the hook is not that we found a particle, even though the particle is what detectors can see. The hook is that empty space in our universe is not featureless, and its structure selects which excitations behave as massive. The Higgs boson is the measurable ripple that confirms the field exists in the way the theory requires, with the right quantum numbers and the right interaction strengths. The deeper actor is the vacuum expectation value that quietly rewrites the spectrum. turning gauge fields into massive carriers, and turning Yukawa parameters into rest masses, we also need to be clear about what mass means here, because the word carries different meanings across physics. For a free relativistic particle, even 2 P2 su C nu please M2 C4, and the mass sets the rest energy and the relation between energy and momentum. In field theory units with C as just 1, the mass is the parameter that sets the pole of the propagator and the curvature of the potential around the vacuum. When the Higgs background changes, those parameters in the effective theory change, and the dispersion relations change with them. In plain language, the vacuum sets how hard it is to excite a field into a particle. This chapter ends by setting the roadmap, because the rest of the film will treat these claims as calculations, not slogans. We start from wave equations and the need for fields, because particles are not fundamental in the same way fields are. We move to actions and Lagrangians as the compact way to encode dynamics, including the constraints imposed by symmetry. We define potentials, vacua, and what it means for a vacuum to be non-trivial, with explicit attention to what is measurable and what is inferred. We then treat spontaneous symmetry breaking precisely, and we show how gauge fields remain consistent while acquiring mass through the Higgs mechanism. We add Yukawa couplings to explain fermion masses and the pattern of Higgs interactions, including why coupling measurements are the real test. We return to the early universe to track how the Higgs vacuum evolved with temperature, and we end by naming what remains unknown. The next step is to build the formal language that makes these claims testable, because physics advances when statements can be falsified. We begin with the simplest field, the simplest action, and the first appearance of mass as a term that symmetries can forbid. From there, the Higgs stops being a headline and becomes a calculation, and the vacuum stops being emptiness and becomes a physical object. Chapter 1 ended with a promise, and it was deliberately spare. The Higgs is a field with a vacuum value, and the boson is a fluctuation. Now we build the language that makes that statement precise, without hiding behind metaphor. Start with the simplest object that can carry a disturbance not through space, but through space-time itself. A field is a function that assigns a number to each spacetime point. Write it as pH in one space dimension, or pH with x, a spacetime 4 vector. On screen, this is almost too plain. A grid, a moving cursor, and a number changing as the cursor slides. Yet that plainness is the point, because the field is the thing that exists everywhere. It is not an object located at one place. It is a rule that gives an answer at every place and time. If we colour the grid by value, the abstraction becomes visual. Bright regions mark where pH is large, dark regions where it is small, and the pattern can drift even if nothing moves like a solid object. The field is closer to a temperature map than to a bead on a wire, except the map covers space-time, not just a surface. A wave equation is a rule for how that function changes, and it is the first hint of dynamics. In non-relativistic form, it can look like T2p, V2 pos 2pH, 1, 0. It is linear, it is local, and it supports superposition of solutions. Linearity means something very specific. If pH1 and pH2 solve the equation, then APH1 plus BPH2 also solves it. That property is why waves can pass through each other and still be described cleanly. It is also why Fourier analysis becomes the natural language for fields. Fourier analysis is not merely a mathematical trick, and it is worth seeing why. Any reasonable disturbance can be decomposed into plane waves with definite wavelength and frequency. In that basis, the differential equation becomes an algebraic condition on each mode, and the modes evolve independently as long as the theory stays linear. Locality is equally concrete, even if it sounds philosophical. The equation relates the field at a point to derivatives at that same point. It does not require instant knowledge of distant regions. In a relativistic theory, locality will become tied to causality. Signals should not outrun light. The wave equation already hints at something important, and it is easy to miss. The field is not a particle trajectory, and it is not a bookkeeping trick. It is the primary dynamical variable, and particles will later appear as its quantized excitations. Historically, this reversal of perspective took time to settle. Classical mechanics trained physicists to track objects, while field theory asked them to track continuous degrees of freedom. Maxwell's equations were an early warning that the field could be more fundamental than the sources. Quantum field theory will make that warning unavoidable. To talk about the Higgs, we need a relativistic field equation, because the standard model is built to respect special relativity. Relativity does not add decoration. It constrains the form of the dynamics through Lorentz invariance. Lorentz invariance means the laws look the same in all inertial frames, even when observers disagree about time intervals and lengths. Space and time mix under boosts, so derivatives must be packaged in a covariant way. The object that replaces 2, is the D'Alembertian. Visually, it helps to watch coordinates tilt. A spacetime diagram rotates in a hyperbolic way, and what used to be time derivative and space derivative reshuffle. The D'Alembertian is the compact operator that survives that reshuffling. It is built to be the same object in every inertial frame, set C, Segret, H, Rap1, to keep the structure visible, because the algebra otherwise hides the physics. Then energy, momentum, and mass share the same units. The metric signature fixes signs, but the physical content is the same across conventions. This unit choice is not a trick so much as a declaration. It says that time and space are measured in compatible units, and that action is measured in pure numbers. When we later restore units, we will recover familiar scales, like 125 GeV for the Higgs mass. The simplest relativistic equation for a real scalar field is the Klein-Gordon equation. It reads, Sachtens plus m2 sampens 0. The constant m is not an afterthought, and it is not a label we attach later. Klein and Gordon wrote down this equation in the 1920s, aiming to merge quantum ideas with relativity. It was a stepping stone, not a final answer, because it did not describe spin-half electrons correctly. Yet it became the prototype for relativistic fields, and it remains the cleanest place to learn the logic. You can motivate that equation from the relativistic dispersion relation, which connects frequency and wavelength. Plane wave solutions take the form P1 Plugging into the equation gives a m2, which is E plus m2. This is not just algebra, because px is the invariant phase. It is the quantity every inertial observer agrees on, even when they disagree about E and P separately. The field's oscillations are therefore tied to geometry, not to any one frame's bookkeeping. That relation is the field theory version of rest mass. When P for 0, the energy is E sub m. The parameter m controls how frequency depends on wavelength, and it controls how hard it is to excite the field. There is another way to see the same content, and it is useful for intuition. A massless field has E, P, so long wavelengths can be arbitrarily low energy. A massive field has a gap. No excitation exists below E, m. That gap is what rest mass means in the spectrum. In classical field theory, m is a parameter in the equation of motion. In quantum field theory, the same parameter becomes the mass of the quanta. The pole of the propagator sits at P2 m2, and experiments measure that pole. A propagator is the field's response function, and it is what appears inside scattering amplitudes. When the denominator approaches 0 at P2 m2, the amplitude spikes in a characteristic way. Detectors do not see poles directly, but they see the resonance patterns those poles produce. This is the first time the film's central question becomes technical, because it stops being purely descriptive. If masses are parameters in field equations, then the Higgs story must explain why those parameters take the values we observe. It must do so without breaking the gauge symmetry that defines the standard model. A differential equation is one way to specify dynamics, and it is the way most of us first meet physics. Modern particle physics uses a more compact method because it keeps symmetries visible. It starts from an action principle. Define the action as S d4xL. The Lagrangian density L is a local function of fields and their derivatives. The physical field configurations make the action stationary under small variations. On screen, the action is a single integral that seems to swallow everything. Yet that is its power, because one object generates the equations of motion. It also tells you what is allowed and what is forbidden, once you demand certain symmetries. For a field, the Euler Lagrange equation becomes ML, MPH, LPHS 0. This is not a stylistic choice. It is the framework that makes symmetries and conservation laws systematic. Noether's theorem sits quietly in the background here, even if we do not invoke it explicitly. Continuous symmetries of the action imply conserved quantities, like energy and momentum. That connection is one reason the action is the preferred language in relativistic theories. Write the canonical Lagrangian for a real scalar field. Use L, san 1, 2, mph, v, ph. The first term is the kinetic term fixed by Lorentz invariance and locality. The kinetic term is also where the metric enters, because Pamph is a Lorentz scalar. It is constructed so that observers in different inertial frames compute the same Lagrangian density. In plain language, it is the simplest relativistic motion energy you can write for a scalar. The second term is the potential, and it carries the theory's most revealing choices. Here it is a function of the field value at a point, not of position directly. In field theory, Vph is an energy density contribution for a static uniform configuration. This is a subtle shift from mechanics, where a potential is often a function of position. Here the position is the value of the field itself, which means the landscape lives in field space. You can picture the field as a coordinate, and the potential as a terrain that coordinate can sit on. V is where the Higgs story will later live, and that is not an exaggeration. The Higgs mechanism is not primarily about the kinetic term. It is about the structure of the vacuum implied by the potential and by gauge interactions. For now, keep it minimal, because we are building a dictionary. Choose a simple quadratic potential, V plus H, skersen, 1 plus 2 mesta 2 plus 1 plus 2. Insert it into the Euler Lagrange equation. You recover, also, plus L plus M plus 2, plus H plus M 0. So the same symbol m appears in two places, and that duplication is meaningful. It is the coefficient in the potential, and it is the mass parameter in the equation of motion. This is already a clue that mass can be read as curvature of energy. To make that statement precise, define what we mean by a vacuum in classical field language. The vacuum is not the absence of fields. It is the lowest energy field configuration allowed by the theory. That definition sounds simple, but it changes the mental picture of empty space. Empty space is not a blank stage with nothing on it. It is a particular configuration of the fields that the theory says exist everywhere. The vacuum is a solution, not a void. Energy comes from the Hamiltonian density, derived from the Lagrangian. For a scalar field, the energy density includes 12 T per pH 2, 12 pH 2, and Vph. A vacuum configuration minimizes the total energy. You can almost see these terms as competing textures in an animation. Time variation costs energy, spatial variation costs energy, and sitting high on the potential costs energy. The vacuum is the configuration that makes all those costs as small as the theory allows. For a uniform vacuum, gradients vanish, and that simplifies the problem. Then the problem reduces to minimizing Vph. The vacuum field value pH 0 is a constant that sits at a minimum of the potential. If V has its minimum at pH 0 as 0, then the vacuum field is 0. If V has its minimum at pH 0, 0, then the vacuum field is non-zero. Both are allowed by the formalism. This is the conceptual pivot we will use later, and it is easy to state carefully. A scalar field can have a constant non-zero vacuum value without selecting a direction in spacetime. A constant scalar does not break Lorentz invariance, because it is the same in every inertial frame. Vector fields are different, and the contrast is instructive. A non-zero vacuum value of a vector would pick a preferred direction, and would violate Lorentz invariance. That is one reason the Higgs must be a scalar in the minimal standard model. The statement is not aesthetic, and it is not optional. Our universe does not appear to have a built-in preferred rest frame in its fundamental laws. If the vacuum carried a vector arrow everywhere, boosts would reveal it, and experiments would have found that violation. Now connect vacuum structure to mass, because this is where the mathematics becomes physically sharp. Consider small fluctuations around a vacuum configuration. Write phx, e scarces ph0 plus ix, where E is a small field. In visuals, the field becomes a surface, and the vacuum becomes a flat plane. The fluctuation is a ripple on that plane, localized in space and time. The key move is that the ripple is not defined in isolation. It is defined relative to the vacuum baseline. Expand the potential in a Taylor series around pH0, V pH0 plus gain, eller svam pitazran plad vin pitazron, plus 1, 2 vin pitazron, 2 plans higher terms. At a minimum, v piazron dagar 0. This is where calculus becomes physical. The first derivative vanishing means the vacuum is stable against small shifts. The second derivative measures how quickly the potential rises when you move away from the minimum. In plain terms, it is the stiffness of the vacuum. The constant term v piazra shifts the vacuum energy. The linear term vanishes at the minimum. The quadratic term controls the leading dynamics of small oscillations. Insert the expansion into the Lagrangian and focus on the terms that are quadratic in I. The quadratic part becomes 1,2 miasism, 1,2 med f2i2, where ma ef2 ställs till gasen pu. The fluctuation obeys a Klein Gordon equation with that mass. This is the clean link we need, and it is remarkably general. Mass is the curvature of the potential at the vacuum. A steeper curvature means a heavier excitation, because the field resists being displaced from its minimum. Another way to say it is spectral. The vacuum defines the lowest energy state, and the curvature defines the energy gap to the first small oscillation mode. That gap becomes the rest energy of the particle once the field is quantized. The Higgs boson will later be exactly this kind of excitation, and this is the heart of the earlier promise. It will be the quantum of X, the fluctuation around a non-zero vacuum value of the Higgs field. The rest of the mechanism is about how other fields feel that vacuum value. Before we quantize, pause on what we have and what we do not have, because the distinction matters for the documentary's tone. We have a classical field with a vacuum configuration and small oscillations. We have not yet introduced particles, creation operators, or measurement outcomes. In the classical picture, a ripple is just a ripple, and it can have any amplitude. In the quantum picture, the ripple comes in discrete packets, and those packets behave like particles in detectors. The mathematics that enforces that discreteness is the quantization step. Quantization is the step that turns field modes into operators, and it is usually presented as a leap. Expand the field in Fourier modes, with coefficients that become operators AP and AP+. Impose canonical commutation relations so the theory has a consistent quantum structure. The Fourier expansion is not just convenience, because each mode behaves like an independent harmonic oscillator. Quantization then becomes the quantization of infinitely many oscillators, one for each momentum, p. The operators AP and OS plus lower and raise the excitation number of those oscillators. After quantization, the vacuum becomes a quantum state Bos 0. It is defined as the lowest energy eigenstate of the Hamiltonian, not as an empty container. The field operator phx acts on that state to create excitations. In the free theory, AP0 is a one-particle state with momentum p. The energy of that excitation satisfies E2's m2. This is how the parameter becomes the measured rest mass of a particle. Even the phrase one particle is a statement about the vacuum. It means one quantum above the ground state, not one tiny object moving through space. The particle is a label for an excitation pattern, and the vacuum is the reference that makes that label meaningful. In an interacting theory, the story is more subtle, and we should say that out loud. The vacuum can be reshaped by interactions, and the excitations can mix. Still, the organizing idea remains. Particles are quanta of fields defined relative to a chosen vacuum. This is why the word vacuum is dangerous in casual speech, because it invites the wrong image. In quantum field theory, the vacuum can contain non-zero expectation values. It can also contain fluctuations, even when expectation values vanish. Write the vacuum expectation value explicitly. D0 CPO px masses can be zero or non-zero, depending on the theory and the phase. When it is non-zero and constant for a scalar, Lorentz invariance can remain intact. That constancy is crucial, and it is testable in principle. If the expectation value depended on position or time, it would break translation invariance and physics would vary from place to place. The standard model vacuum does not do that, at least not in any way we have observed. This is the bridge back to the 2012 hook, and it is worth slowing down for the cadence. A resonance is a particle excitation. The deeper claim is that the vacuum itself has structure, encoded in a non-zero field value that persists everywhere. You can visualize that claim without mysticism. The detectors at the LHC do not measure a vacuum directly. They measure tracks, energies, and decay products that appear when an excitation is created and then disappears. Yet the properties of those excitations reveal the baseline they were excited from. On screen, the collision point blooms, and then the event display resolves into arcs and clusters. Curvature in a magnetic field reveals momentum, timing layers reveal flight paths, and calorimeters light up with deposited energy. The vacuum never appears as a picture, yet it leaves fingerprints in every reconstructed mass peak. Now return to the action, because it is where we will later embed gauge symmetry. The action formalism is not only a way to get equations of motion, it is the natural place to impose symmetry requirements that restrict which terms are allowed. For a real scalar field, the allowed renormalizable terms are limited, and the limitation is a clue about what can be fundamental. The kinetic term is fixed. The potential can include m2 speeds 2 and LPH 4 plus a constant. Odd powers can be forbidden by a symmetry like pH. PSG renormalizable here means that the couplings have non-negative mass dimension in 4 spacetime dimensions. In plain language, it means the theory can remain predictive at high energies, without requiring infinitely many new parameters. That criterion shaped the Standard Model's construction in the 1960s and 1970s. The quartic term matters because it stabilizes the potential at large field values. Without it, a negative m2 would make the energy unbounded below. With it, a negative m2 can produce a stable minimum at non-zero pH0. On screen, the potential curve changes character. A simple parabola becomes a Mexican hat profile in the more general case. Even for a single real scalar, it becomes a double well. The minimum moves away from the origin, and the vacuum becomes a choice. This is the prototype of spontaneous symmetry breaking in scalar theories, and it is the simplest place to say what that phrase means. The Lagrangian can be symmetric under pH, while the vacuum chooses either plus to PL or PL d'Abdas. The symmetry is present in the equations, but not in a specific vacuum. We will not use analogies for this choice because the mechanism is already clear in the math. It is a statement about minimizing energy in field space. Different minima correspond to different vacua, and excitations are defined by expanding around one minimum. A thought worth holding is how much of what exists depends on that choice. If you expand around one vacuum, the excitations look like particles with certain masses. If you expand around another, the labels can change, even though the underlying Lagrangian is the same. The vacuum is not a background detail, it is part of the definition of the spectrum. In gauge theories, the same logic becomes more constrained, and we are approaching the edge of this chapter. The Higgs field is not just any scalar. It carries gauge quantum numbers, and its vacuum value must be discussed with care. Still, the scalar prototype teaches the essential move, and it is the move we will reuse. Identify the vacuum by minimizing an energy functional. Expand the field around that vacuum. Read off masses from the quadratic terms in the expanded Lagrangian. In the scalar case, the mass of the excitation is V alum mass pH0. In the gauge case, masses for other fields can appear when the vacuum value sits inside covariant derivatives and Yukawa couplings. The vacuum acts like a constant background that multiplies other fields. This is where the central question starts to sharpen into a constraint. If gauge symmetry forbids explicit mass terms, then mass must emerge from allowed interaction terms once the vacuum is chosen. The Higgs field provides a gauge-invariant way to write those interactions. But we are not there yet, and we should keep the promise of the chapter's title. We still need to be explicit about Lorentz invariance, because it is the constraint that keeps the vacuum story consistent. A vacuum that is uniform in space and time is translation invariant, and that invariance is part of why momentum is conserved. A scalar vacuum value is also Lorentz invariant, because it does not transform into something else under boosts. That is why a constant does not define a preferred frame. The vacuum can still break internal symmetries, and this is the subtlety that will matter later. Internal symmetries act on field components, not on spacetime coordinates. A vacuum can select a direction in an internal space while remaining Lorentz invariant. That distinction will matter when the Higgs becomes an SU2 doublet. The vacuum will pick a direction in the space of weak isospin components. Lorentz symmetry will remain intact, while part of the gauge symmetry will be hidden in the spectrum. For now, keep the prototype real and scalar, because it keeps the camera focused. It lets us define vacuum, fluctuation, and mass without extra indices. It also lets us state the key claim in one line. The Higgs boson is the quantum of fluctuations around a vacuum value. The phrase vacuum value must be handled precisely because it can mean two related things. In classical language, it is the field configuration that minimizes energy. In quantum language, it is the expectation value of a field operator in the ground state. These two pictures match in the appropriate limit, and that matching is part of why the prototype works. When quantum fluctuations are small, the vacuum expectation value tracks the classical minimum of an effective potential. When fluctuations are large, the effective potential includes quantum corrections, and the vacuum can shift. Those quantum corrections are not decorative, and they are not optional at high precision. Virtual particles in loops modify the potential's shape, and the modification depends on the energy scale at which you probe the theory. In practice, this means parameters like L and even the effective curvature can run with scale. This is not a side issue because it touches the Higgs directly. The Higgs potential in the standard model is not only a classical function, it is an effective object that runs with energy scale, and it can be modified by new physics. Even in this minimal chapter, we can name the consequence without wandering. The Higgs mass we measure is related to the curvature of the effective potential at the vacuum. The value 125 GeV is a measurement of that curvature, not a measurement of the vacuum energy. Vacuum energy is a separate parameter, and it connects to the cosmological constant problem. The Higgs sector contributes to vacuum energy, but the observed cosmic acceleration is far smaller than naive field theory estimates. That mismatch is real, and it is unresolved. We do not solve that here, and we should not pretend we do. We only mark it as part of the mystery, because the vacuum is physical in more than one sense. It shapes particle masses, and it also seems to gravitate, yet our accounting does not close. Now tighten the thread back to the documentary's hook, because the narrative must stay anchored. In 2012, we found evidence for a scalar excitation. The deeper implication is that the underlying field exists, and that its vacuum configuration is a property of empty space. A particle bump in a detector is not the vacuum itself. It is a transient excitation above the vacuum. The vacuum is the baseline state that defines what counts as an excitation and what counts as mass. This chapter's job is to make that baseline state mathematically clean, and to do it with minimal machinery. A vacuum is a minimum of energy. A field is a function on space-time. Dynamics come from an action. Mass appears as a parameter and as curvature. Now we can state the next step without hand-waving, while still keeping the details for later chapters. The standard model Higgs is not a real scalar field. It is a complex multiplet with gauge interactions, and its potential is chosen so the vacuum has non-zero magnitude. When that vacuum is inserted into the Lagrangian, some gauge bosons acquire mass terms from Redempth-2. Fermions acquire mass terms from Yukawa couplings. The gauge symmetry remains in the action, even though the vacuum is not fully symmetric. Those statements will be derived later, not asserted as slogans. For now, the prototype has done its work. It has shown how a vacuum can be non-trivial, how mass can be read from quadratic terms, and how excitations become particles after quantization. One more clarification keeps the mystery honest, because the Higgs is often described in ways that mislead. A non-zero vacuum expectation value does not mean the field is a classical substance filling space. It means the ground state of the quantum theory is not centered at zero field value. The vacuum is a state, not a material, and that distinction matters when we imagine space filled with Higgs. It is defined by the Hamiltonian and by boundary conditions. Its properties can be inferred from scattering, from spectra, and from how fields propagate. That is why the Higgs boson matters, and why its discovery was more than a missing particle. It is a measurable handle on the vacuum structure, because its mass and couplings encode the shape of the potential near the minimum. Measuring those properties is how we learn what the vacuum is. Now we pivot toward the electroweak theory. The next chapters will add gauge fields, local symmetry, and the specific Higgs multiplet. We will show exactly how the vacuum reorganizes degrees of freedom without breaking the underlying gauge invariance. The mystery remains, but it is now constrained by the mathematics we have built. If empty space has structure, it must be describable by a field configuration that minimizes an action. If mass is not inserted by hand, it must emerge from that vacuum through allowed terms. Chapter 2 ends with the minimal dictionary, and it is worth hearing it as a checklist. Field means pH or X. Lorentz invariance means equations built from M and Drönder. Action means S, Max, D, Biox, L. vacuum means lowest energy configuration, possibly with 0, and Higgs boson in this language will mean one thing. It is the quantum excitation of fluctuations around the Higgs field's vacuum value, once that vacuum is identified inside the full gauge theory. Chapter 2 built a dictionary for fields, actions, vacua and masses, and it did so with deliberate precision. Chapter 3 uses that dictionary to show how symmetry can survive, even when the vacuum does not. The goal is not poetry, but a controlled surprise. The equations keep their order while the ground state quietly changes the cast. Start with the precise definition of symmetry and field theory, because every later claim depends on it. A symmetry is a transformation of the fields that leaves the action invariant, not merely the picture in your head. Write fields collectively as phix, and write the action as cn, whereas d force tx, l, ph. A transformation is a symmetry of On screen this can look almost austere, an integral sign, a Lagrangian density, and a compact condition of equality. Yet that equality is doing heavy work, because it is a statement about a functional that generates the equations of motion. Through the principle of stationary action, ds becomes dynamics, so invariance of S means the dynamics do not change. In other words, the symmetry is written into the rules of the game, not into any one outcome. This definition is stricter than a vague idea of looking the same, and the strictness is the point. It is a statement about which terms are allowed in L, because non-invariant terms are forbidden. When you build a model, symmetry becomes a filter. Only certain combinations of fields survive. That filtering is why symmetry is not decoration, and why it can predict what interactions must be absent. There is also a practical reason for this emphasis, especially in quantum field theory. The Lagrangian is the object we quantize, and its symmetries organize the spectrum and the interactions. They control selection rules, conservation laws, and the structure of radiative corrections. Even when we later talk about vacua and particles, we are still reading consequences of In the quantum theory, invariance of the action is also the reason a change of variables in the path integral does not alter physics. That technical statement sounds abstract, but it is the backbone of why symmetries constrain amplitudes. When the symmetry is exact, it survives quantization unless an anomaly intervenes, and we are not invoking that here. For this chapter, assume the symmetry is genuine, and watch what the vacuum alone can do. Separate two kinds of symmetry, because the Higgs story depends on the difference. A global symmetry uses parameters that are constant in space-time, so the same transformation is applied everywhere at once. A local symmetry uses parameters that can vary with x, and that requirement forces gauge fields to exist. The distinction sounds technical, but it changes what redundancy and physical even mean. For a global symmetry, the transformation might be x with a constant. For a local symmetry, the same form becomes x, and now the phase can twist differently at different points. The kinetic term then fails to stay invariant unless derivatives are replaced by covariant derivatives. Visually, you can imagine the phase as a color wheel painted across spacetime, and local symmetry allows that wheel to rotate independently at each point. Why does the kinetic term care so much about AX? Because EM acts on everything, including the spacetime dependent phase. When A is constant, EM plus EM is 0, and nothing new appears. When A varies, plus H produces an extra term proportional to pH, and that term ruins invariance. The cure is to introduce a gauge field that shifts in exactly the right way, so the covariant derivative transforms cleanly. You can show that cure in one crisp line because the structure is almost inevitable. Replace JASM with D, Skern, M plus JAS AGEM, and demand that A and WEM transforms to cancel the unwanted term. The mathematics reads like bookkeeping, but the visual feels like compensation. An extra field appears to protect a symmetry. That is why gauge fields are not optional decorations in a locally symmetric theory. This chapter stays mostly on the global side because it reveals the vacuum logic cleanly. The next chapter will show what changes when the symmetry is local, and why that changes the particle content. Keep that boundary explicit because it is where the standard model avoids unwanted massless scalars. For now, We want the simplest stage where the vacuum can misbehave while the action stays symmetrical. Now define the object that will control everything, and do it without metaphor. The potential V is the part of the Lagrangian that depends on fields but not on derivatives. In a relativistic scalar theory, the Lagrangian typically looks like L for kinetic terms, V, so V contributes directly to the energy density. For static, uniform configurations, minimizing energy reduces to minimizing V. The vacuum is a field configuration that minimizes the energy, and for uniform vacua it sits at a minimum of V. This is a useful simplification, and it is also a physical statement about what we mean by ground state. A vacuum is not an empty box with nothing inside, because fields are always present as operators. Instead, it is the lowest energy state consistent with the theory's rules. When we say the field takes a value in the vacuum, we mean the vacuum expectation value of the field operator is non-zero. It is also worth noticing what we are quietly assuming when we talk about the vacuum. We are assuming translation invariance, so the vacuum does not vary from place to place. We are also assuming the vacuum is stable, meaning small disturbances do not run away. Those assumptions are not cosmetic, because they let us interpret small fluctuations as particles with definite masses. We want the simplest renormalizable potential for a complex scalar field with a continuous symmetry. Take one complex field PHX with a global U1 symmetry pH, Renormalizability in 4 dimensions restricts the potential to terms up to quartic order. Symmetry restricts it to depend only on P2, because P2 is invariant under phase rotations. Renormalizability is not an aesthetic rule, and historically it was treated as a survival constraint. In 4 spacetime dimensions, operators of dimension higher than 4 come with couplings that have negative mass dimension, and they typically make ultraviolet behavior harder to control. Keeping only terms up to PNGS4 is the minimal choice that still allows interactions. It is also the choice that kept early quantum field theories calculable, long before effective field theory made the deeper logic explicit. In modern language, you can hear a second message in that restriction. Higher dimension operators can exist, but they are suppressed by some heavy scale, and they become small at low energies. So the quartic potential is not merely convenient, it is the leading term in a controlled expansion. That perspective will matter later, because it tells you why this simple potential is a reliable first approximation. So write the most general renormalizable U1 invariant potential. V pH PS4 plus constant. The constant shifts vacuum energy and will not affect the location of minima. The parameters Durstu and L are real, and stability will constrain their signs. On screen you can show the potential as a simple polynomial in the radius p because the phase never appears. Stability is not a stylistic preference, because an unstable potential is not a theory with a ground state. If L were negative, the quartic term would drive V to -infinity for large OS PX. Then there is no lowest energy state, and the theory has no stable vacuum. So require L is 0, which ensures the potential rises at large field values. With L fixed positive, the sign of M2 decides the vacuum structure, and this single sign is the hinge of the entire phenomenon. The same symmetric action can produce either a symmetric vacuum or a degenerate set of asymmetric vacua. In the documentary's visuals, this is where the plot splits into 2 distinct landscapes. One is a simple bowl centered at the origin, and the other has its lowest points arranged away from the center. Case 1 is M2, 0. Then V increases as PHX grows from 0, because both terms are non-negative. The unique minimum occurs at PHB of 0. The vacuum expectation value is 0, and the vacuum is invariant under the U1 symmetry. In this phase, the symmetry is not only a property of the equations, but also a property of the ground state. In this phase, expanding around the vacuum is straightforward and almost mechanical. Write PHX as small fluctuations around 0, and the quadratic term M2 Saupastandu gives a positive mass parameter. The mass comes from the curvature of V at the minimum, which is the second derivative with respect to the field. The symmetry is present in both the laws and the vacuum state, so the excitations organize themselves into symmetric multiplets. If you pause on that curvature, you can make the connection to ordinary oscillators feel concrete. A steep potential well means a strong restoring force, and a strong restoring force means a higher oscillation frequency. In relativistic field theory, that frequency becomes a mass, because energy at zero momentum is E = up. The vacuum is quiet, and the spectrum is simple. Case 2 is m2, 0, and now the same formula hides a different geometry. The quadratic term is negative near the origin, and V initially decreases as phx moves away from 0. The quartic term eventually dominates at large .phx and pushes V upward, because else is 0. The competition produces minima at non-zero, just phx, and the origin becomes unstable in the sense that it is not the lowest energy point. It is worth pausing on what negative m2 really means, because it is often misheard as a literal negative mass. In the unbroken phase, m2 would be interpreted as a mass squared for small oscillations about phx 0. When m2 is negative, it tells you that pH word 0 is not the correct expansion point. The theory is not sick because the quartic term stabilizes it, but the naive interpretation of the quadratic term is no longer valid. Visually, the origin is like a perfectly balanced peak rather than a valley. A tiny nudge does not bring you back, it sends you sliding away toward lower energy. The field does not want to be at 0, because 0 is not the lowest point available. The vacuum is found not by preference but by minimization. Find the minima by minimizing V with respect to .phx, and do it in a way that keeps the symmetry visible. Treat R, Serchen, PHM as a non-negative real variable. Then VIR, Cern 2 dem, Jan dos, Chan 4. The stationary points satisfy div document Yam to OR plus fall R3, 0. This equation is simple enough to show on screen, while the plot of VR makes the meaning immediate. There is always a stationary point at R 0. From 2, 0, our R is a maximum rather than a minimum, because the curvature there is negative. The non-zero solutions satisfy a wu or nu 2 well. Define V by V nu well, so the minima occur at R 2. The factor of 2 is bookkeeping, but it will keep later mass formulas clean. This V is not introduced by hand as a new field, and it is not a separate assumption. It is a derived scale set by the parameters already present in the potential. It is the magnitude of the vacuum field value in the broken phase. In a quantum theory, V becomes the vacuum expectation value that reshapes the particle spectrum. Now the key structural fact appears, and it is more important than any one algebraic step. The minima are not a single point in field space. They form a continuous set because the potential depends only on phx, not on the phase. Every field value with phx evu 2 has the same potential energy. The plot in 2 real dimensions shows it clearly. A ring of equally low points surrounding the origin. Parameterize that set explicitly. Write phx v2 e diphers for any constant phi. Each phi labels a different vacuum configuration, all with the same energy. The action remains invariant under U1, but any chosen vacuum is not invariant under the full group. The symmetry still exists as a transformation, yet it no longer leaves the vacuum unchanged. This is spontaneous symmetry breaking stated precisely, without slogans. The Lagrangian is symmetric under pH, E. The vacuum state, once chosen, is not invariant because it has a definite phase. The symmetry is not removed from the equations, but it is not manifest in the ground state. The laws are symmetric, while the state that solves them is not. Historically, this idea did not arrive first through particle physics. It was understood earlier in condensed matter systems, where the ground state of a magnet picks a direction, even though the microscopic rules are rotationally symmetric. The field theory language then made the concept portable, and it became a tool for high-energy physics. That migration matters because it shows this is not a trick. It is a general feature of many body and field systems. In the mid-20th century, this portability became a turning point. Ideas from superconductivity and collective behavior suggested that the vacuum could behave like a medium with structure. Particle physics then asked a daring question. What if empty space itself carries an order parameter? The Higgs story inherits that question, and it answers it with field theory. The phrase, "the vacuum chooses," is a shorthand for a physical statement, and it deserves to be unpacked. The theory has multiple degenerate ground states, and the system occupies one of them. Once one vacuum is selected, excitations are defined relative to that choice, and the spectrum reflects it. The vacuum is not passive background. It is the reference point for what counts as a particle. In infinite volume, different vacua are separated by superselection in the idealized limit. Local operations cannot rotate the entire vacuum everywhere without costing energy in gradients. If you try to change the phi in one region while keeping it fixed elsewhere, the field must vary in space, and that spatial variation adds energy. In practice, the universe ends up in one domain, and that selection looks like a direction in internal space. That gradient energy is not a footnote, because it is what makes domains and defects conceivable. A slowly varying X corresponds to a long wavelength excitation, and it can be extremely cheap energetically. That cheapness is already whispering the existence of a massless mode. The vacuum manifold is not just a set of points, it is a landscape you can move along. Hold on to that whisper, because it is about to become one of the most consequential ideas in modern physics. That massless mode hiding in the landscape isn't a mathematical curiosity. It's the seed of a mechanism so powerful it explains why particles have mass at all. And it's the reason a machine the size of a city was built underground in Europe to hunt for a single particle. We'll get there later in this video, and when we do, this cheap little excitation will turn out to be anything but cheap. But first, we need to make the vacuum itself precise, in the full quantum language. Now define the vacuum expectation value in the quantum language, because the vacuum is a state in Hilbert space. In the chosen vacuum Zuru, the field operator has Ruppes-Dual Vosov 2. Translation invariance requires this expectation value to be constant in X, since a vacuum cannot single out a location. Lorentz invariance is preserved because pH is a scalar, so a constant value does not pick a space-time direction. We can simplify the bookkeeping by choosing a convenient representative vacuum. Because the theory is symmetric, we can pick Thiafion0 as a reference. Then the chosen vacuum has gyms of V2, real and positive, without changing any physical predictions for invariant quantities. This step is like choosing coordinates in field space, and it is allowed because all the Thi are physically equivalent before we introduce boundaries or explicit breaking. This choice is not a gauge fixing yet, because we are still discussing a global symmetry. It is simply selecting one vacuum from the degenerate set to define fluctuations. The underlying U-1 symmetry still exists as a transformation relating different vacua. In the next chapter, when the symmetry becomes local, an analogous choice will acquire a new meaning. Now expand the field around the chosen vacuum and identify the physical modes, because particles are small oscillations about the ground state. Write the complex field in terms of two real fields. Use PHX, Jriastor 1 tier 2, V plus Erges X, Pilstudgerskas X. Here, H is the fluctuation along the radial direction in field space, and A is the fluctuation orthogonal to it. This decomposition is not an analogy, and it is not a metaphorical radius and angle. It is a coordinate choice in the two-dimensional real field space of RePH and MPH. The vacuum sits at a point with coordinates V2, 0, and we are expanding around that point. In a visual, the camera can hover over the ring of minima, then settle on one point, and then zoom into tiny vibrations. Insert this expansion into the potential, and keep terms up to quadratic order, because quadratic terms define free particles. Start from V, 2 suspicios 2, los PKRs 4, compute, PRs 2, za 1 PR2, za plus de H, 2 plus 1 PR2, kya kjast. Expand V in powers of H and Ihag, and keep constant, linear, and quadratic pieces. The linear terms must vanish if V is chosen at a minimum, because a true minimum has no first-order slope. That condition reproduces the relation Vsusgam M2L. This is the same minimization condition, now appearing as cancellation of tadpole terms in the expanded Lagrangian. In diagram language, it means the vacuum does not emit a single H quantum, because the expansion point is stable. The quadratic terms determine the masses of small excitations, because mass is the coefficient of the field squared in the Lagrangian. The coefficient of H2 is the curvature of V in the radial direction. The coefficient of H2 is the curvature in the angular direction. In the broken phase, these curvatures are not equal, because the vacuum manifold is flat in one direction and curved in the other. Compute the radial mass explicitly, because this is where the Higgs-like mode emerges. After expansion, the quadratic term for H is 1, 2, 2 love 2, H2 in the potential. In the Lagrangian, that becomes 12 MH2H2 with MH2 Ertul of 2. The mass is fixed by the second derivative of V at the minimum, which is why we keep calling it curvature. This is the Higgs-like excitation in the simplest model. It is a scalar mode with a non-zero mass set by L and V. It is not the vacuum itself, and it is not the symmetry breaking. It is the quantized fluctuation along the direction that changes pH, and therefore changes the energy at second order. The geometry gives you an intuition that stays correct even when the algebra becomes heavier. Along the radial direction, you climb out of the minimum so the energy rises immediately, and that rise produces a restoring force. A restoring force produces oscillations, and oscillations with a restoring force produce a massive particle. Along the angular direction, at least in the global case, the energy does not rise at leading order. Now look at the orthogonal mode K. In the broken phase with a global U1, the quadratic term for ek vanishes. The potential depends only on PSIM, so moving along the circle of minima costs no potential energy at leading order. That flat direction gives to 0. On screen, you can show a tiny displacement that slides along the ring without climbing. This is not an accident of algebra, and it is not a special feature of quartic polynomials. It is the local expression of the global degeneracy of vacua. The continuous symmetry implies a continuous manifold of minima, and the tangent directions to that manifold are massless at the classical level. The masslessness is the spectrum's way of remembering that the vacuum could have been chosen differently. State the theorem that makes this unavoidable, because it is one of the most powerful general results in the subject. Goldstone's theorem says that when a continuous global symmetry is spontaneously broken, the spectrum contains massless excitations. Each broken generator produces one massless mode, under standard assumptions of locality and a well-defined vacuum. The theorem is not a model-specific trick, it is a structural consequence. In this model, U1 has one generator and the vacuum breaks it. So there is one Goldstone boson, represented here by skirched X. It is not optional, and it is not a matter of choosing a different parameterization. It is a physical consequence of the symmetry structure, and it appears no matter how you label the fields. Make the logic explicit in field language, because the theorem can sound like magic unless you see the mechanism. The action is invariant, so there is a conserved Noether current for the global symmetry. The vacuum is not invariant, so the charge does not annihilate the vacuum. That mismatch forces a massless pole in certain correlation functions, which is the Goldstone particle. In scattering language, it means there is a long wavelength excitation that costs arbitrarily little energy. You can even feel that long wavelength limit in the visuals. Let θcx vary slowly across space, and the field barely climbs the potential at all. The energy sits mostly in gradients, and as the wavelength grows, that gradient cost shrinks. A mode whose energy can be made arbitrarily small is, in particle language, massless. In the expansion, you can see the same result as a statement about curvature. The potential has a minimum along a circle, so the second derivative along the tangent direction is 0. A 0-second derivative means no mass term for that mode. The masslessness is the geometry of the vacuum manifold translated into the spectrum, and the translation is done by the quadratic Lagrangian. This is the moment where the documentary's tone should tighten, because the implications are both elegant and dangerous. The laws remain symmetric, but the vacuum is not. The vacuum is a state, and it carries information that is not visible in the Lagrangian's form. The spectrum is the vacuum's fingerprint, and it reveals the hidden choice. If you linger on the visuals, the contrast becomes almost cinematic. The action is a clean, symmetric expression, unchanged by rotation in internal space. The vacuum, however, is a single point on a ring, and it breaks the symmetry by existing. How much of what we call particle properties is really a property of the vacuum they live in? Now widen slightly to match the standard model structure without leaving the chapter's scope. The Higgs field in the standard model is not a single complex scalar. It is a complex SU2 doublet, which means 4 real field components. The potential is still built from the same principle, because renormalizability and gauge symmetry restrict the form. The same logic that filtered terms for U1 filters terms for SU2 as well. The same renormalizable structure appears. V GCR saith them 2. F plus FTF 2 with L and all 0. The difference is that F has internal indices, and the symmetry group acting on it is larger. the vacuum manifold becomes higher dimensional, and the counting of Goldstone modes becomes crucial. You can foreshadow that counting by showing 4 components turning into one massive radial mode plus several flat directions. Even before gauge fields enter, the global version of this symmetry breaking would predict multiple massless scalars. The number equals the number of broken generators. This is already a warning sign because we do not observe a zoo of massless scalar particles coupled to electroweak physics. If they existed with appreciable couplings, they would show up as long-range effects and missing energy channels. Keep the narrative anchored to what we have proven, because the temptation is to jump ahead. A negative quadratic term does not mean instability. If the quartic term is positive, it means the origin is not the vacuum, and the vacuum sits at non-zero field magnitude. The vacuum expectation value is a constant that minimizes the potential, and it breaks the symmetry of the vacuum state. The symmetry of the Lagrangian remains intact, even as the ground state stops reflecting it. There is also a subtle point about language, and it matters for clarity. We say the symmetry is broken, but nothing in the equations has been damaged. The symmetry is still there as a map between equally valid vacua. What changes is which vacuum the world occupies, and which excitations are small and cheap around that choice. The break is in the state, not in the rules. Now connect back to the central question without solving it yet. The Higgs boson in the standard model will be the massive radial excitation around a non-zero vacuum value. The masses of other particles will come from expanding the full Lagrangian around that vacuum, because terms that looked like interactions become mass terms when one field is replaced by its VEV. But the symmetry involved is not merely global, and the Goldstone modes cannot remain as physical massless scalars. This is the next problem, and it is not cosmetic. If the electroweak symmetry were only global, spontaneous breaking would force massless Goldstone bosons. Those modes would mediate long-range forces or appear as new light particles, and experiments would have seen them. The absence of such particles is not a small discrepancy. It is a decisive clue about what kind of symmetry the standard model uses. So something different must happen in the real theory. The standard model symmetry is local, and local symmetry changes the meaning of the would-be Goldstone fields. The same degrees of freedom appear, but they are reorganized with the gauge fields. What looked like an extra particle in the global theory becomes, in the local theory, part of the gauge field's physical polarization content. Hold the mysterious fact in place for the transition, because it is the hinge of the Higgs mechanism. The vacuum picks a direction in field space, and that choice is real. Yet the underlying laws remain symmetric, and the theory does not lose consistency. The resolution will be that local symmetry allows the Goldstone modes to be absorbed into gauge fields, changing the particle content without breaking gauge invariance. End the chapter by stating what has been built and what remains, because the structure is now complete. We defined symmetry as action invariance and separated global from local. We constructed the renormalizable potential, V, L appears with L0. We showed N2 gives a symmetric vacuum, and N2 gives degenerate minima at P2 with V L. We expanded around a chosen vacuum and found one massive mode with 2. We found one massless mode from the flat direction, and we identified it as the Goldstone boson required by a broken continuous global symmetry. Now the standard model's need is clear. We need symmetry breaking to generate masses, but we cannot keep unwanted massless scalars. Next chapter, the symmetry becomes local, and the vacuum's choice stops creating extra particles. The same mathematics will be used, but the interpretation of the modes will change, and that change is the Higgs mechanism. The Higgs story is not a story about adding mass by hand, like bolting weight onto a machine. It is a story about what gauge symmetry allows a quantum field theory to contain, and what it refuses to tolerate. The refusal is not stubbornness or taste, it is the mathematical price of consistency. In the standard model, symmetry is not merely a decorative principle that makes equations look elegant. Gauge invariance is the condition that keeps interacting spin-1 fields consistent, unitary and renormalizable when we push them to extreme energies. When that condition fails, the theory does not simply become ugly, it becomes unreliable. It starts to predict answers that depend on arbitrary choices of description, which is a warning sign physics takes seriously. Visually, imagine a clean sheet of space-time drawn as a grid, with arrows representing a vector field living at every point. The arrows can be relabeled without changing the physics, and that freedom is the symmetry we're about to test. A subtle camera move can make the grid feel like a fabric, while the arrows shimmer like compass needles. The surprising fact is that this freedom, which sounds like a choice of language, dictates whether mass is allowed. Start with the simplest gauge theory, a U1 field AM coupled to matter. This is the structural template for electromagnetism even before we name the photon. The field strength is defined as Fmd, just man. Nam, a combination built to cancel the pieces that depend on how we label the field. It is the first hint that the theory cares more about relationships than about raw components. In a visual sequence, the camera can sweep across the symbols as if they are etched into glass, while the background shows rippling field lines. Fm is not just notation, it encodes the electric and magnetic fields, and it is the object that survives every allowed relabeling. You can show the anti-symmetry directly, with M and N swapping places and the sign flipping. That survival is the clue, because physics must live in what cannot be gauged away. Write the gauge transformation as AM plus may x. The parameter AX is local, so it can vary at each spacetime point rather than staying constant across the universe. This locality is the defining leap from a global symmetry to a gauge symmetry. It is also the step that turns symmetry into a structural constraint on dynamics. If A were constant, the transformation would be a simple phase shift with no derivatives attached. But because AX can twist differently at different points, the derivative term becomes unavoidable, and it changes how we must build the theory. Local symmetry is a demand that the physics remain unchanged even as our description flexes point by point. In imagery, the labels on the arrows slide and rotate across the grid, yet the measurable patterns remain fixed. The pure gauge Lagrangian is L, This term is gauge invariant because Fm is unchanged by AM plus may, and the anti-symmetry removes the extra derivative pieces. That invariance is not a miracle, it is engineered into the definition of Fmn. The theory is built so that the redundancy is respected at the deepest level. In a more physical picture, Fmn measures curvature in the gauge potential, the way a magnetic field measures the curl of a vector potential. Pure gauge changes are like adding a gradient, and gradients do not contribute to curl. The mathematics is compact, but the intuition is familiar. You can visualize a landscape where adding a constant slope changes coordinates, yet leaves the curvature unchanged. Now try to add a naive mass for the gauge field, as if it were an ordinary particle field. The Proca term is L mass, Dishan, and by dimensional analysis it looks innocent. It is local, it is Lorentz invariant, and it is quadratic, so it seems like the simplest possible mass. In a purely classical mindset, it feels like a harmless modification. Under the gauge transformation, am plus sem, am plus sem may, extra terms appear that cannot be written as a total derivative, which means they cannot be discarded as boundary effects. The Lagrangian itself changes, and the symmetry is explicitly broken. The theory starts to treat ARX as if it were a physical field, even though it was supposed to be mere redundancy. You can almost see it on screen as the expression expands, revealing cross terms like amma and mamma. Those terms depend directly on the arbitrary function AX. So the theory would start treating a choice of description as if it were physical. That is the opposite of what a gauge theory is supposed to do. It is like a map insisting that north must be painted red, and then calling the paint a force. So, 1 is not gauge invariant for local AX. A hard mass term breaks the symmetry that defines the gauge theory, and it does so in the most direct way. The theory loses its built-in redundancy, and with it goes a crucial layer of consistency. What looked like a simple addition becomes a structural wound. This is not a minor bookkeeping issue, and it is not just a philosophical preference. Once gauge invariance is broken, the quantum theory typically loses renormalizability and predictive control at high energy, because the cancellations that tame infinities no longer occur. The theory begins to demand an ever-growing list of new counterterms. Each new counterterm is a confession that the original Lagrangian was not enough. Historically, this was not an abstract worry. In the decades after quantum electrodynamics proved renormalizable, Physicists learned to treat renormalizability as a practical survival rule for quantum field theories. A theory that cannot be renormalized is not necessarily wrong, but it stops being predictive without an explicit ultraviolet completion. In the mid-20th century, this distinction separated workable theories from beautiful dead ends. The deeper reason is the structure of spin-1 propagation. A massive vector has 3 physical polarizations, while a massless gauge boson has 2, because the longitudinal mode is not physical when gauge redundancy is present. Gauge symmetry is what lets us remove unphysical components without violating Lorentz invariance. In quantization, that removal shows up as constraints and gauge fixing, rather than as a literal deletion. In a visual metaphor, a massless gauge boson is like a wave that can vibrate in 2 transverse directions, always perpendicular to its motion. A massive vector is like a rigid arrow that can also oscillate along its direction of travel. That extra degree of freedom is precisely the one that causes trouble when introduced carelessly. It is the hidden passenger that becomes dangerous at high speed. If you insert a mass by hand, the longitudinal mode behaves badly in scattering. Amplitudes grow with energy and violate unitarity unless new structure appears, because the longitudinal polarization vector scales like momentum over mass. At high energy, that scaling turns into an amplifier. The very feature that makes the vector massive becomes the source of runaway behavior. Unitarity is not an optional aesthetic rule. It is the statement that probabilities add up to 1, and it is encoded in the S matrix being unitary. When longitudinal modes drive amplitudes upward, the theory predicts probabilities larger than 1, which is a clear signal that the description has broken down. In a documentary frame, you can show a probability meter creeping past 100%, an impossible reading. Gauge symmetry is that structure. It enforces cancellations between diagrams and restricts counterterms, so ultraviolet behavior stays under control even when many processes contribute. What looks like a delicate conspiracy is actually a consequence of symmetry. The theory is not fine-tuned by hand, it is disciplined by redundancy. This is why gauge invariance is not merely about choosing a convenient gauge like Lorentz gauge or Coulomb gauge. Those are computational choices, while gauge invariance is a statement about the underlying redundancy. The redundancy is what keeps the quantum theory from counting unphysical states. A good gauge choice is like a good coordinate system, but the existence of coordinates is the deeper point. The same logic appears in the matter sector, where local symmetry forces interactions. The rule is simple but profound. Replace ordinary derivatives with covariant derivatives so that derivatives transform properly under local changes of phase. The interaction is not added by hand, it is demanded. In other words, the symmetry does not merely permit forces, it manufactures them. For a U1 charged field PES, define d mean m plus ig am. The kinetic term Ixgendempses automatically contains the interaction G-D-Gem-S, along with the free kinetic term Tgem-Mes. The coupling constant G is not an afterthought. It is the strength of the gauge connection. You can think of AM as the field that keeps local phase comparisons meaningful. On screen, the covariant derivative can appear as a highlighted substitution, with them fading into DM as AM slides into place. The narration can linger on the idea that the gauge field is a compensator, introduced so local symmetry can exist. Without AM, local symmetry would fail as soon as derivatives act. A close-up can show the derivative catching the local twist and cancelling it. So local symmetry is not only a constraint, it is also a generator of the coupling between currents and gauge fields, and it tells us the form of that coupling. The theory does not allow arbitrary interactions, it allows the ones that preserve the redundancy. This is why gauge theories feel rigid, almost inevitable, once the symmetry is chosen. Noether's theorem gives the global version. A global phase PES, gas implies a conserved current gem, and gauge fields couple to that current. In the U-1 case, that current is essentially electric charge flow. Historically, this connection helped turn symmetry from a mathematical curiosity into a physical organizing principle. But the local theory goes further, and the language shifts. Gauge invariance becomes a redundancy in description rather than a physical transformation, and physical quantities are gauge invariant combinations like fair-min and S-matrix elements. The field AM itself is not directly observable. Even the potential's value at a point is not sacred, because only gauge invariant information survives measurement. This redundancy is what makes the theory consistent. It removes unphysical degrees of freedom and keeps probabilities positive in the quantum Hilbert space. Because negative norm states are artifacts of an over-complete description, gauge fixing and ghost and quantization are technical tools to manage that redundancy, not signs of failure. The bookkeeping looks strange, but it is the cost of keeping the physics clean. Now extend the idea to non-abelian symmetry, where the gauge field carries the charge it mediates. The group relevant to the weak force is SU2, and it is qualitatively different from U1. In SU2, the generators do not commute, so the gauge field interacts with itself. That self-interaction is not optional, it is forced by the algebra. Introduce 3 gauge fields. Do you am with a yanda 1 to 2.3. The generators to satisfy ter, tep, gan, EABCTC, which encodes the algebra of rotations in an internal space. That internal space is not ordinary space, but it behaves mathematically like one. The commutator is the signature that the symmetry has a built-in twist. Visually, you can imagine 3 coloured components of the W field, braided together as the camera rotates around them. The non-commutation means that performing transformations in different orders leads to different results, and that non-commutativity leaves fingerprints in the dynamics. A simple animation can show 2 rotations applied in swapped order, ending in visibly different orientations. The message is that the symmetry itself has structure, and the fields must respect it. The non-abelian field strength is Famn, Mwan, Nwam, Jabquib Muosin. The last term is the signature of self-interaction, and it has no counterpart in simple electromagnetism. It is the mathematical reason non-abelian gauge theories are so rich. In visuals, that cubic term can glow, emphasizing that the field talks to itself. Gauge transformations now mix components. WAM transforms with an inhomogeneous derivative term and a rotation in group space, so the fields are not independent labels. The symmetry ties them together into a single structure. What looks like 3 separate vectors is really one object living in a 3-dimensional internal space. The Yang Mills-Lagrangian is L lust 1,4 f F. Gauge invariance again forbids a simple mass term, 1,2 M2 M, for the same reason it failed in U1. The inhomogeneous part of the transformation ruins the invariance. The theory refuses to let you pick out a preferred magnitude for W without paying a price, so the pattern is rigid. For both abelian and non-abelian forces, local gauge symmetry tightly controls which operators can appear in L, and it does so more strictly than naive dimensional analysis suggests. The symmetry is a gatekeeper. It does not merely guide the theory, it polices it. Renormalizability sharpens that control. In 4 dimensions, the standard model keeps operators of dimension 4 or less as the leading terms, because higher dimension operators are suppressed by some heavy scale. This is the logic of effective field theory, even if we do not name it explicitly here. The low-energy Lagrangian is a disciplined expansion, not an arbitrary list. A hard gauge Boson mass is dimension 2 and seems harmless by power counting, yet it violates gauge symmetry, and that violation ruins the renormalizable structure, because the dangerous high-energy behavior returns through the longitudinal polarization. The problem is not the dimension, it is the broken redundancy. The theory can forgive many things, but it will not forgive losing its cancellations. This is the first tension we need to feel. The theory of forces wants gauge symmetry, and gauge symmetry wants massless gauge bosons, because massless vectors fit naturally into the gauge framework. Yet nature presents a counterexample in the weak force. The weak interaction behaves like a gauge theory, but its carriers are heavy. But the weak force is short range, and short range implies massive mediators. Experiments measure MW80, GeV, and MZes91 GeV, and those numbers are not subtle deviations. They are bold facts, written into decay rates, scattering cross-sections, and the very existence of beta decay. A short-range force is a force whose influence dies quickly with distance, and mass is the simplest reason. In a visual montage, detectors light up with tracks that curve in magnetic fields, while reconstructed invariant masses peak sharply at the W and Z values. These peaks are not philosophical arguments, they are data repeated across experiments and decades. The short range is visible too, in the way weak processes are rare unless energies are high. Even the emptiness between events becomes part of the story. So the standard model must do something more subtle than adding to womb. It must generate effective masses while keeping gauge invariance of the Lagrangian, so the theory remains unitary and renormalizable. The mass must emerge from a gauge invariant structure. The trick cannot be cosmetic because the high-energy behavior will expose it. Now specify which gauge symmetry is at stake. The electroweak theory is based on SU2 LXU1Y, a product group that combines weak isospin and hypercharge. This structure was not guessed casually. It was built to match the observed pattern of weak and electromagnetic interactions. It is a framework that explains why the photon and Z are related yet distinct. There are 4 gauge fields in the unbroken description: 3 WWIM for a SU2L with coupling G, and 1 BM for U11 with coupling G. At this stage, none of these fields is yet the photon or the Z. They are the symmetry fields before the vacuum chooses a direction. The physical particles will be mixtures, but the theory begins in a symmetric basis. The covariant derivative acting on a field in some representation is d chel m plul ik to y m plul ig to y2 bm. The hypercharge y labels the u1y representation, and it is assigned so that the theory reproduces known electric charges after symmetry breaking. The derivative is where the entire electroweak interaction is encoded. Every vertex in the Feynman rules is, in a sense, hiding inside dem. This derivative is the core of the electroweak structure. It fixes the allowed interactions and it encodes which fields feel which forces, because the generators and charges decide how each field transforms. Once dm is written down, much of the theory is no longer negotiable. The symmetry has already made most of the decisions. The subscript L is not decoration. SEU2STL acts only on left-handed fermions, which is an experimentally established chiral feature of the weak interaction. The weak force distinguishes left from right in a way electromagnetism does not. The universe, at least in weak processes, has a preferred handedness. Historically, this was one of the great shocks of 20th century physics. Parity, once assumed to be a sacred symmetry, was found to be violated maximally in weak processes, and the electroweak theory had to build that fact into its foundation. The L in SU2L is the mathematical memorial of that discovery. It is a reminder that nature does not always respect our aesthetic expectations, so we must treat chirality precisely. For a Dirac fermion P's, define PL1 PL plicha and PL kia wa PR pli with PL adia plicha yan 1 G5. 2. These projection operators separate the field into components that transform differently under Lorentz transformations and, crucially, under the gauge group. In visuals, the field can split into 2 streams labelled L and R, moving through different gates. These are independent fields in the gauge theory. They can transform differently under SU2LXU1Y, and in the standard model they do because the data demand it. The theory is chiral at a fundamental level. That chirality is not a small correction. It is built into the representation content. Take one lepton family as the template. The left-handed fields form an SU2, doublet L, skin NL, EL, T with hypercharge YL. The doublet structure means the neutrino and electron are paired under weak isospin rotations. A rotation in this internal space can turn one into the other, which is why charge currents exist. The right-handed charged lepton ER is an SU2 singlet with a different hypercharge E. In the minimal standard model there is no NR, which means the neutrino begins as a purely left-handed participant in weak interactions. That absence will matter when we ask how masses can appear. Even before we solve anything, the field content already hints at constraints. Quarks follow the same pattern. The left-handed quarks form a doublet Q, SES, UL, DL, T, while UR and DR are singlets with distinct hypercharges. The doublets are the fields that feel the charged weak current, the interaction that changes one flavour into another. On screen, you can show a W boson connecting U and D lines, emphasising that the doublet is the reason the connection exists. On screen, a table can appear with columns for SU2L representation and hypercharge, and rows for L, ER, Q, UR, and DR. The pattern looks almost like bookkeeping, but it is the bookkeeping that decides which terms are legal. Each entry is a lock, and gauge invariance is the key that must fit. The audience can feel the rigidity because the table leaves little room to improvise. This chiral assignment is forced by data. Only left-handed fermions participate in charged current-weak interactions, and parity is maximally violated. The theory does not have the freedom to treat left and right symmetrically without contradicting experiment. The symmetry is chosen to match reality, and then reality constrains everything else. Now recall what an ordinary fermion mass term looks like. A Dirac mass is a lem. M bul plia, plus sim bul plwell. It is a coupling between left and right components, and it is local and Lorentz invariant. In plain terms, it ties the two chiral halves into one massive particle. This term couples left and right components in a way that is completely natural in a non-chiral theory. It is gauge invariant only if Pessel and Pessar transform in conjugate representations that make Pessel-Pessar a singlet. In other words, the product must be neutral under every gauge factor. If any part carries leftover charge, the term is forbidden. In QED, that works because both chiralities carry the same electric charge. The electron's left and right components transform the same way under U1 cis dm, so Pessel Didar is neutral, and the mass term is allowed. Electromagnetism does not care about chirality. The gauge symmetry and the mass term coexist peacefully. In the electro-weak theory, Pessel and Pessar carry different SU. 2 Pessel XU modify quantum numbers. The left component sits in a doublet, while the right component is a singlet, and their hypercharges are chosen to reproduce observed charges. The mismatch is structural, not accidental. It is the same mismatch that makes weak interactions chiral in the first place, so the obstruction is immediate. For the electron, L is a doublet and ER is a singlet, so Pessel-Pessar is not an SU2 L singlet. Under an SU2 L transformation, L rotates into itself, but ER does not rotate at all. The mass term would change under the symmetry, which is exactly what a gauge theory forbids. Even if you ignore SU2L, hypercharge still matters. The product must have total Y equal to 0, and the standard model assignments do not allow it for a bare mass term. Gauge invariance checks every factor, and it only takes one failure to forbid the operator. The symmetry is like a strict editor, rejecting any term that breaks the grammar. Therefore, a bare Dirac mass term for charged leptons and quarks is forbidden by gauge invariance. The symmetry that makes the weak theory consistent blocks ordinary masses, as if the theory is insisting that mass must be earned rather than declared. This is the same kind of refusal we saw for the gauge bosons. The pattern is now unmistakable. The very principles that make the theory work also seem to deny the world we observe. The gauge bosons face the same barrier. A term like 1 m2 and explicitly breaks SU2L, and a term breaks U1Y. The very symmetry that defines the fields is violated by the simplest mass you might write. In a visual, the symmetry group icons can crack when the mass term is overlaid. You might try to write a mixed mass term between W3 item and Behrman. That also breaks the gauge symmetry unless it arises from a gauge invariant structure, because the mixing would single out directions in group space by decree. The theory will not accept that kind of favoritism at the level of the Lagrangian. If a direction is chosen, it must be chosen by the vacuum, not by our pen. So the pre-Higgs electroweak Lagrangian seems to predict a world with massless W and Z analogues, plus massless quarks and charged leptons. It would be a world where the weak force is long-range, like electromagnetism, and where atoms would not look the way they do. This is not a small discrepancy. It is a full-scale collision between principle and observation. That world is not our world. Weak interactions are short-range, and fermions have measured masses spanning MeV to hundreds of GeV, from the electron to the top quark. The spectrum is not only massive, it is uneven, hinting at hidden structure. Why should one Yukawa coupling be tiny and another enormous if mass is truly emergent? This is where the central question becomes unavoidable. What is the Higgs boson precisely, and how can a gauge theory generate mass without breaking its defining symmetry? If gauge invariance is the rulebook, then the Higgs must be a way of following the rules while changing the outcome. The mystery is not just technical, it is conceptual, because it asks what empty space is allowed to do. We also inherit a second constraint from Chapter 3. If a continuous symmetry is broken globally, Goldstone's theorem produces massless scalars, one for each broken generator. These Goldstone bosons are not optional, they are a theorem's promise. In visuals, you can show small ripples propagating without cost, like waves on a perfectly frictionless surface. A naive spontaneous breaking of SU2, L, X, U, 1, Y as a global symmetry would generate several Goldstone bosons. We do not observe such light scalars coupled to weak currents, and we would have noticed them in decays and scattering. Their absence is as constraining as the presence of W and Z masses. It is a silence that carries information. So the mechanism must do three things at once. It must preserve gauge invariance of the Lagrangian, produce massive W and Z, and avoid physical Goldstone particles. Each requirement is strict, and together they feel almost contradictory. How can symmetry be both present and apparently broken, without leaving behind the usual debris? The only way forward is to use a field that transforms under the gauge group. Its interactions must be gauge invariant, and its vacuum must be non-zero, so that empty space itself carries a kind of structured background. The vacuum must choose a direction without the Lagrangian choosing one. That distinction, laws versus ground state, is where the loophole lives. Then masses can appear not as explicit symmetry-breaking terms, but as consequences of expanding gauge invariant operators around that vacuum. The symmetry remains present in the equations, yet the spectrum reorganizes because the ground state is not symmetric in the obvious way. The distinction between the symmetry of the laws and the symmetry of the vacuum becomes decisive. In a visual, the equations stay unchanged while the background field settles into a particular orientation. This is the structural promise of the Higgs sector. The gauge symmetry remains exact in the Lagrangian, while the vacuum reorganizes which combinations of fields look massive. What changes is not the rulebook, but the state the universe inhabits. The theory keeps its redundancy, yet the particles behave as if something has stiffened the vacuum. We can already see where the masses will hide. A term like dust2 is gauge invariant, and if f has from 0, it produces quadratic terms in U sub m and bm when we expand around the vacuum. Quadratic terms in a vector field are exactly what a mass looks like. The mass is not inserted, it is revealed. In a visual reveal, the covariant derivative acts on the vacuum value, and the gauge fields appear as if they are pulling against a constant background. The mathematics turns into imagery. The vacuum behaves like a medium that resists certain gauge motions. That resistance is what we interpret as mass. The camera can linger on the idea that nothingness has become an active participant. Those quadratic terms look exactly like masses for certain linear combinations. One combination remains massless, and that survivor will be the photon, the field associated with an unbroken U1 symmetry. The theory must leave electromagnetism intact, because we observe a massless photon with exquisite precision. Even a tiny photon mass would reshape long-range electromagnetism, and nature does not permit it. Fermion masses will hide in Yukawa terms. A gauge-invariant coupling like Y, E, LF, E, R plus HC becomes a Dirac mass once F is replaced by its vacuum value, because the Higgs field can carry the missing quantum numbers. The Higgs acts as a bridge between left and right. It supplies exactly what the forbidden Baire term lacked. Notice what is happening conceptually. The mass term is not written as m-b, which gauge symmetry forbids, but it emerges as y-p after the vacuum is chosen. The parameter y is a coupling, and the mass becomes a derived quantity. The theory trades an explicit mass for an interaction with the vacuum, but this chapter stops before the solution. Here we only make the constraint explicit and unavoidable, so the next step feels necessary rather than decorative. The narrative tension is the point, because it tells us why the Higgs is not optional. If the Higgs did not exist, something else would have to do its job, and it would still need to satisfy these same rules. Gauge symmetry forbids naive masses for spin-1 fields. Chiral electroweak assignments forbid naive Dirac masses for fermions. These are not separate problems. They are two faces of the same demand for local gauge consistency. The standard model is not being difficult, it is being coherent. Yet the measured spectrum contains massive W and Z and massive fermions, while the photon remains massless. The standard model must reconcile these facts without sacrificing consistency, or else it collapses into a patchwork of broken rules. The reconciliation must be structural. It must preserve the cancellations that make the theory predictive, so we end with a controlled tension. Empty space must contain a field configuration that changes the spectrum, while the gauge symmetry remains built into the Lagrangian. The vacuum must do the work that explicit mass terms are forbidden to do. The question is not whether the vacuum can be active, but what form that activity must take. Next chapter, we introduce the Higgs field inside SU 2LXU1Y and show how its vacuum value generates masses and absorbs Goldstone modes. The mystery is not whether the Higgs exists, but why this particular mechanism is the only one that satisfies every constraint at once. When the pieces finally click together, the earlier refusals will look less like obstacles and more like guidance. We ended with a refusal that feels absolute, almost like a law carved into the equations. Gauge symmetry forbids explicit masses for W and Z, because a naive mass term would spoil the very redundancy that keeps the theory consistent. Yet the weak bosons are heavy in every detector record, and the photon remains exactly massless across every precision test. That tension is not a minor bookkeeping problem. It is a structural dilemma about what symmetry really means in a quantum field theory. Is symmetry a property of the Lagrangian, written once and for all, or is it a property of the vacuum that the universe actually occupies? The electroweak theory forces us to separate those ideas, and that separation becomes the loophole. This chapter builds the loophole precisely. Mass appears from a vacuum configuration that preserves gauge invariance of the Lagrangian, even while it reshapes what we call particles. The symmetry stays in the rules, while the spectrum reorganizes around the chosen ground state, quietly but decisively. Visually, think of the Lagrangian as a blueprint etched in glass, perfectly symmetric under rotations of internal labels. Then imagine the vacuum as a particular orientation of that glass in space, selected without changing the etched pattern. The pattern remains symmetric, but the chosen orientation makes some directions special, and those special directions become measurable. In the frame, the glass can rotate smoothly, yet the room's lighting makes one angle stand out. Start with the electroweak gauge group, the compact statement behind a vast experimental program. It is SU2LXU1Y, with gauge fields WMA for CU2L and BM for U1Y. The couplings are G for CU so as 2L and G for U1Y, and their different strengths already hint at later mixing. Even the notation carries history because it encodes decades of scattering data in a single line. The SU2L factor acts only on left-handed fermions, which is why the subscript L matters physically. The U1Y factor assigns hypercharge, a quantum number that looks abstract until it recombines into electric charge after symmetry breaking. The gauge fields are not optional decorations, they are required once we demand local symmetry, because local symmetry forces compensating connections. In plain terms, if you allow the internal orientation to vary point by point, you must introduce fields that track the change. It is worth lingering on what local means, because it is the source of both power and constraint. A global symmetry rotates all fields the same way everywhere, like turning a rigid object as a whole. A local symmetry allows different rotations at different space-time points, like twisting a fabric differently at each location. That freedom would make ordinary derivatives misbehave, so the theory introduces gauge fields to restore consistent comparisons between neighbouring points. Introduce the Higgs field content with no extra story, because the mathematics is already dramatic. The Higgs is a complex SU2 doublet Fx, meaning it has two complex components that transform together. It carries hypercharge Y Kyrgyzstan 2, so it transforms under both factors, and that single choice will later guarantee a massless photon. The doublet is the minimal option that can break the symmetry in the needed pattern without breaking too much. You can picture F as a two-component column vector whose entries are complex fields, each varying with space-time. 4 real degrees of freedom live inside it, even before we decide what the vacuum does. Those degrees of freedom will not all survive as particles, and that is the first hint of the mechanism. On screen, the two complex components can be shown as 4 sliding dials, each capable of oscillation. Write the Higgs sector terms we actually need, the minimal set that does the entire job. The Lagrangian pieces are dV2 Vf, where the first term is kinetic and the second is potential energy. The potential is Vf. M2 F plus Vz. plus test F plus F just with L less 0, so the energy is bounded from below. That inequality matters, because without it the theory would have no stable lowest energy state to expand around. That potential is deceptively simple, and historically it was chosen for a reason. With only renormalizable operators in 4 dimensions, this is the most general polynomial potential for a complex doublet consistent with the gauge symmetry. The coefficients m2 and L are not predicted here. They are parameters to be fixed by nature. In the language of effective field theory, this is the leading structure allowed by symmetry at low energies. There is also a visual reason it is useful for narration. A quadratic term sets the curvature near the origin, while the quartic term controls the walls far away. Together they create either a single bowl or a ring-shaped trough, depending on the sign of M2. That sign is not a minor detail, because it decides whether the vacuum is symmetric or structured. Define the covariant derivative in the representation of F, because this is where gauge symmetry hides its power. Dem gern M plus IG, TAR2, Boame, Pal I Gugum, Y, Bem, where tau are the Pearly matrices. For the Higgs doublet, Y, del 1 tok 2 is fixed by the charge pattern we later want. The Pauli matrices are not decoration either. They are the concrete generators of SU2 in the fundamental representation. The covariant derivative is more than a notational trick, because it is the mechanism that enforces local symmetry. Under a gauge transformation, M-phi alone would transform incorrectly, but Demph transforms the same way as F itself. That is the technical meaning of gauge invariance, and it is why Dorf Anstus 2 is allowed while a Proca mass term is not. The derivative becomes a kind of guided comparison, corrected by gauge fields, so the theory stays consistent. The potential decides whether the vacuum is trivial or not, and the sign of M2 is the pivot. For M2 os 0, the minimum is at F sium 0, so the vacuum is symmetric and nothing dramatic happens. For M2 os 0 ohm, the minimum occurs at non-zero F plus F, and the vacuum becomes a whole family of equivalent choices. In that second case, the lowest energy state is not a single point, but a continuous set. It helps to visualize Vive as a landscape drawn over field space. When M2 is 0, the landscape is a bowl with its lowest point at the origin. When M2 is 0, the landscape becomes a Mexican hat, with a circular trough of minima at a fixed radius, flat along the trough, steep toward or away from it. The flatness along the trough is where the Goldstone story begins to whisper. Minimize the potential in the usual way, because the vacuum is just the field value that minimizes energy. The condition is FLSS4 M2 2L at the minimum, so the magnitude is fixed even though the direction is not. Define V by V2 as M2L, so the vacuum magnitude is V2. The vacuum is therefore characterized by a scale, not by a unique orientation. That factor of 2 is not cosmetic, because it makes later mass formulas come out cleanly. The vacuum expectation value V will be the single scale that sets the size of electroweak masses, and it will appear everywhere once we expand around the vacuum. In this sense, V is the hidden ruler inside the theory. It is the number that quietly converts dimensionless couplings into masses with units. Now choose a specific vacuum representative, because calculations need a concrete point on the trough. Use gauge freedom to align the vacuum in a convenient direction in SU2 space, like choosing coordinates to simplify geometry. Take F, 0, V2t, which selects the lower component as non-zero. In visuals, the field space ring can be shown, then one point on it is highlighted as the chosen reference. This choice is not explicit symmetry breaking, and that distinction is the heart of the loophole. The Lagrangian remains gauge invariant under 2Lxu1y, and every term still respects the same local redundancy. The vacuum is not invariant under the full group, and that is the only change. The rules remain symmetric, but the ground state does not share the full symmetry. In a global symmetry, picking a vacuum direction would be a physical statement about the system, because global transformations relate distinct states. In a gauge symmetry, many transformations relate descriptions of the same physical state, so the language must be careful. The vacuum breaks the symmetry, in the sense that not all gauge transformations leave Fm unchanged, but the gauge principle itself remains intact. The redundancy is still there, and it still does its job of protecting consistency. Connect V to an observable scale, because the vacuum is not just a philosophical choice. In the standard model, V is fixed by the Fermi constant from muon decay, a low-energy process measured with exquisite precision. The relation is V' dos 2GF 12246 GeE, which turns a decay rate into a vacuum scale. It is striking that a tabletop-scale lifetime measurement points to a field value hundreds of times heavier than a proton. Historically, this connection was a triumph of consistency rather than invention. Long before the Higgs boson was seen, the weak interaction strength was already known from beta decay and muon decay. The electroweak theory then demanded a specific V to reproduce that strength, and the number 246 GeV became a quiet prediction embedded in the formalism. In the background, this was also the era when gauge theories were being rehabilitated as quantum theories, after earlier doubts about their mathematical control. Now show where gauge boson masses come from, because this is the moment the refusal dissolves. They come from the gauge invariant kinetic term def-2, not from any forbidden explicit mass operator. When F is replaced by its vacuum value, that term becomes quadratic in gauge fields, and quadratic terms are mass terms. The theory does not add mass by decree, it reveals mass as a consequence of expanding around the true ground state. The key is that the vacuum is constant in space-time, so derivatives do not act on it. What remains is the gauge connection, acting on a non-zero field value, and that produces something that looks exactly like mass. Gauge invariance is never violated, because the original term was gauge invariant from the start. The mass is therefore hidden in plain sight, inside an allowed operator. Compute dm acting on the vacuum, keeping the logic visible. Since F is constant, MF, 0, so no ordinary kinetic piece survives. Only the gauge connection terms remain, so DAF depends linearly on WMA and BM, with coefficients set by G, Gis and the generators. In a diagram, the derivative arrow fades out, and the gauge field arrows remain bright. Insert FO into Tjestjestnul Dmef Tns2, and the structure emerges without any guesswork. The result is a sum of terms like WWMA, WMB, and WM3BM and BMBM, all multiplied by VDM2. These are exactly mass terms, produced without writing any Proca operator and without sacrificing gauge invariance. The vacuum has converted interaction structure into a mass matrix. At this point, the visuals can slow down and become almost mechanical. The covariant derivative becomes a matrix acting on the vacuum vector, and the product, Dmf-2, becomes a quadratic form in the gauge fields. What looked like pure symmetry bookkeeping becomes a concrete mass matrix in front of the camera. You can almost hear the click as the abstract symbols lock into place, separate charged and neutral directions, because the algebra organizes itself that way. The charge fields are built from W1 and W2, which act like raising and lowering operators in SU2. Define W plus mias, W1m I W2m, twi, and the charge sector immediately diagonalizes. This is the same mathematical move used in angular momentum, now repurposed for gauge fields. This step is not arbitrary, because W1 and W2 always appear in the combination that rotates one component of the doublet into the other. The complex combinations, W+, are the fields that carry electric charge after symmetry breaking. Even before we name electric charge, the mathematics already suggest a pair of conjugate states. In the visual language, two real oscillations combine into one rotating phasor. The mass term for W+ emerges cleanly, almost as if the theory wanted it to be seen. From d miasvis, or as 2, the coefficient of W plums Wm is G2 v2 with no mixing left in that sector. Therefore MW comes to G v sas 2, a simple result that ties mass directly to coupling and vacuum scale. The mass is proportional to the same G that controls the W's interaction strength. Notice what this means physically, stated in plain language. The W mass is not a free parameter once G and V are known, because the mechanism links them. The same interaction that makes W couple to left-handed currents also sets the size of its mass term after the vacuum is chosen. The boson's heaviness is therefore not an extra feature, it is the shadow of its own coupling. The neutral sector mixes W3 and B, and this is where the photon hides. The vacuum produces a mass matrix in the W3-B basis, because both fields couple to the neutral component of the Higgs doublet. Diagonalizing that matrix defines the physical neutral bosons, and it also reveals one exactly massless combination. In the frame, two waves overlap, then separate into a heavy mode and a light one. Define the weak mixing angle, the compact way to describe this diagonalization. Set tan θw tas just g, which encodes the relative strength of the two gauge interactions. Then define the orthogonal combinations zem and am that diagonalize the quadratic terms, separating massive from massless. The angle is not chosen for aesthetics, it is forced by the requirement that the mass matrix be diagonal. Write the combinations explicitly, because the names Z and photon are earned here. U3M, sin bm, while am, sin plus, cos bm. The mixing is not a metaphor, it is a literal rotation in field space. The rotation angle is measured in experiments, which means the algebra becomes a number in the real world. Read off the z mass from the diagonalized term, and the pattern matches the w result with a twist. The coefficient becomes g via ru plus g2, v24 for zemz, so the mass is fixed. Therefore mz han v2, g2 plus just 2, which is larger than mw because it involves both couplings. The z is heavier because it is built from both gauge sectors at once. One can already see a relationship that experiments famously confirm. Because cos the ww is g, g2 plus g on 2, the theory predicts MELW as MEMZ cos the UNDW, a tight link between masses and mixing. That link becomes a precision test because radiative corrections shift it in measurable ways. In practice, this is why the electroweak theory became a laboratory for quantum loops, not just tree-level elegance. Explain why the photon remains massless in the same step, because the absence is as important as the presence. The am combination has no quadratic term from Dempf-Gowron 2, so it does not acquire mass from the vacuum. That happens because one generator remains unbroken by the vacuum, leaving one exact gauge symmetry intact. The photon's masslessness is therefore not an accident, it is a protected consequence. Identify that unbroken generator precisely, because this is where hypercharge becomes electric charge. The vacuum preserves U Haussmann generated by Q T3 plus Y, the specific linear combination that leaves F unchanged. The gauge field that couples to Q is am, so am stays massless and becomes the photon. In a clean visual, the generator arrow labelled Q passes through the vacuum unchanged, while the others are blocked. This is the central structural point, and it is easy to miss if one focuses only on formulas. A gauge-invariant vacuum can break SU, 2 sus L, XU as 1Y, down to U bears 1, EM, leaving a smaller symmetry that still acts locally. The broken directions acquire massive gauge bosons, while the unbroken direction remains a massless photon. The world keeps electromagnetism as an exact long-range force, while the weak force becomes short-range. Pause on the strangeness of that outcome because it reshapes intuition. The vacuum is not empty, because it carries a non-zero field value that selects a direction in internal space. Yet the equations remain gauge invariant, because the vacuum does not alter the Lagrangian symmetry, only the state around which we expand. What looks like symmetry loss is really a change in which symmetries are manifest in the ground state. There is also a subtle visual contrast worth emphasizing. Before symmetry breaking, the gauge fields are like four identical massless messengers, distinguished only by internal labels. After symmetry breaking, three of them become heavy, and one remains weightless, yet the underlying blueprint never changed. The vacuum has acted like a prism, splitting one symmetric description into the particles we actually observe. Historically, this logic was assembled in pieces, and each piece solved a different worry. In the early 1960s, spontaneous symmetry breaking was understood in condensed matter and global field theories, but it seemed to imply unwanted massless scalars. The electroweak theory needed a way to break symmetry without leaving those scalars behind, and the gauge version of the mechanism provided it. The key insight was that gauge symmetry changes what counts as a physical excitation. It is useful to remember the climate of that period because it explains why the result felt risky. Quantum field theory had produced spectacular successes, yet many theorists worried that massive vector bosons were mathematically inconsistent at high energies. The Higgs mechanism was not only a clever trick, it was a rescue operation for the entire electroweak program. The later proof of renormalizability made that rescue official, turning an idea into a framework. Now make the Goldstone issue explicit because Chapter 3 set the trap, and it still matters. Spontaneous breaking of a continuous symmetry produces massless Goldstone modes in a global theory, and that result is general. The electroweak theory cannot leave physical massless scalars behind, because they would have shown up long ago, so the mechanism must explain both mass generation and the disappearance of Goldstones, parameterize the Higgs field with would-be Goldstones, so we can see them instead of talking around them. Right first x plus x ta sec v, 0, v plus h us x, 2t, which separates angular from radial motion in field space. The three fields k are the angular directions, while hx is the radial fluctuation. This decomposition makes the geometry of the vacuum manifold explicit. This parameterization is like switching from Cartesian coordinates to polar coordinates on the Mexican hat trough. The vacuum fixes the radius, and the Xi describe motion along the trough, where the potential is flat at tree level. In a global theory, flat directions correspond to massless excitations, and those excitations are the Goldstones. The radial direction, by contrast, feels the curvature of the potential, and therefore can be massive. In a purely global theory, those Xa would be physical Goldstone bosons, and their masslessness would be protected by symmetry. They would remain as massless scalars in the spectrum, coupling to other fields in ways that are difficult to hide. That is not what experiments see, and it is not what the standard model contains. The absence of such scalars is therefore a clue that the symmetry must be gauged, not merely global. In a gauge theory, the interpretation changes in a way that feels almost like a magician's reveal, but it is just redundancy. The fields Xi can be removed by a gauge transformation, because gauge transformations act locally and can unwind the angular dependence. This is not deleting physics, because gauge transformations relate redundant descriptions of the same physical configuration. What disappears is not a measurable particle, but a coordinate choice. It is worth asking a careful question here, because it prevents a common misunderstanding. If the Xi can be gauged away, were they ever real particles to begin with, or were they always coordinates? The answer is that in a gauge theory, they are gauge-dependent field components, and only gauge-invariant observables decide what is physical. If you cannot define an asymptotic gauge-invariant one-particle state, you do not have a particle in the observable spectrum. State the gauge choice that makes it concrete, because abstraction can hide the mechanism. In unitary gauge, choose the transformation that sets X to 0 everywhere, so the Higgs field becomes simple, then fix becomes 0 volpHak, 2t, with only one real scalar fluctuation left. The field content looks suddenly minimal, but the underlying degrees of freedom have merely been reorganized. After this gauge choice, the Lagrangian contains explicit mass terms for W and Z, and they look as ordinary as any massive vector theory. It also contains the remaining scalar Hx, which is the Higgs Boson field that survives as a particle. The would-be Goldstones no longer appear as separate particles, because their degrees of freedom have been reassigned. The equations have traded 3 scalar directions for 3 longitudinal vector modes. Explain where those degrees of freedom went, without leaning on metaphor. A massive vector boson has 3 physical polarizations, including a longitudinal mode that a massless gauge boson does not have. A massless gauge boson has 2 physical polarizations, because gauge invariance removes the unphysical components. When the vacuum is non-zero, the theory consistently supplies the extra polarization states required by massive vectors. Count degrees of freedom before symmetry breaking, because the accounting is the cleanest proof that nothing mysterious is added. There are 3 massless W fields and 1 massless B field, giving 3 cus 2 plus 1 cus 2 sus just 8 gauge degrees of freedom. The Higgs doublet has 4 real degrees, giving 12 total. The number 12 is the budget, and the mechanism must spend it without overdrawing. Count degrees of freedom after symmetry breaking, and watch the numbers rearrange rather than change. There are W+, W, and Z, each massive with 3 polarizations, giving 3 plus 3 plus 3 chaos 9. The photon remains massless with 2, giving 11, and the Higgs scalar H adds 1, giving 12 total. The ledger balances exactly, which is why the mechanism is not a sleight of hand. The accounting closes exactly, and that closure is not a coincidence. 3 scalar degrees from F become the longitudinal polarizations of W pluses, W and Z, which is why those bosons can be massive without violating gauge consistency. The remaining scalar degree is the physical Higgs boson, a genuine excitation of the vacuum magnitude. The vacuum has therefore reshaped which excitations are counted as independent physical modes. Emphasize the meaning of eaten without metaphor, because metaphors can mislead at this point. The Goldstone fields are not physical particles in a gauge theory, and they never appear in gauge-invariant observables as asymptotic states. They are gauge-dependent coordinates on the vacuum manifold, and they can be traded for vector field components. The trade is enforced by the structure of the covariant derivative and the gauge-fixing procedure. This trade is visible in the equations, especially when we avoid unitary gauge for a moment. In gauges where XA are present, they mix with W and Z through derivative couplings, which look like mx times gauge fields. After gauge fixing, that mixing reorganizes into the longitudinal polarization states, and the propagators reflect the new massive spectrum. The mathematics shows the reassignment explicitly, rather than hiding it behind words. The visual here can be almost anatomical, like watching a skeleton assemble. A massless gauge field has only transverse vibrations, but once the vacuum is non-zero, the field can oscillate longitudinally as well. The missing longitudinal piece is supplied by the would-be Goldstone direction, and the combined object behaves like a consistent massive vector. The new polarization is not an add-on. It is built from degrees that were already present. Connect this to the earlier unitarity problem, because the mechanism is not only about elegance. The longitudinal modes that made massive vectors dangerous at high energy are now controlled, because their interactions are tied to the same gauge-invariant structure that produced the masses. The Higgs sector supplies precisely the additional contributions needed so scattering amplitudes do not grow without bound. The vacuum choice therefore stabilizes the theory's high-energy behavior rather than destabilizing it. This is one reason the mechanism is so constrained and so testable. If you try to give W and Z masses by hand, you generally lose renormalizability and predictive power. If you generate their masses through a gauge-invariant vacuum, the high-energy behavior is tamed by symmetry relations among couplings. Those relations are not optional, and they become targets for precision measurements. The Higgs mechanism is therefore not a permission slip to break gauge symmetry, and it is not a loophole that weakens the theory's principles. It is a way to keep gauge symmetry exact while changing the vacuum, so the redundancy still protects consistency. The theory remains renormalizable in the same sense as the unbroken gauge theory, even though the particle content looks different. The symmetry is still doing its policing even when the spectrum looks asymmetric. Now isolate what the Higgs mechanism is in one clean definition that matches what we actually did. It is the re-expansion of a gauge-invariant Lagrangian around a vacuum with von zero, chosen from a degenerate set of minima. That re-expansion produces gauge Boson mass terms and removes physical Goldstones from the spectrum. In practice, it is a controlled change of variables around the true ground state. Also, isolate what it is not, because confusion is persistent and often encouraged by casual language. It is not particles gaining mass by moving through a medium, as if the vacuum were a fluid that drags on them. It is not a drag force, and it is not a classical resistance because nothing is slowing particles down. The vacuum does not act like molasses, and mass is not friction. Mass here is a property of the spectrum around the vacuum, and the spectrum is defined by the quadratic part of the Lagrangian. The vacuum expectation value changes which field combinations have quadratic terms, and those terms define the particle masses as propagator poles. In other words, mass is read from how fields oscillate around the vacuum, not from how they travel through it. If the vacuum changes the curvature of the energy landscape, it changes the natural frequencies of oscillation. Return to the central question and tighten the stakes, because the entire chapter is answering a single challenge. We asked how mass is allowed without breaking the theory's symmetry principles, and why the photon is spared. The answer is that gauge invariance constrains the Lagrangian, not the vacuum state that minimizes the energy. The vacuum can be structured while the rules remain symmetric. The vacuum breaks the symmetry down to a subgroup, but the gauge redundancy remains, and that is why the theory does not collapse. Physical predictions stay gauge invariant, even though intermediate calculations can look different in different gauges. The mass terms are not inserted, they are derived, and the photon's masslessness is protected by the unbroken U1 neo-m. The theory, therefore, keeps both consistency and the observed pattern of masses. There is a deeper observation hiding here, and it is worth stating plainly. The vacuum is not merely empty space, because it carries a structured field configuration that affects what excitations can exist. When we say the vacuum has a value V, we are saying the lowest energy state already contains a field condensate, and particles or ripples on top of it. The emptiness of space is in this sense an active ingredient in the spectrum, and that raises a thought-provoking question that the visuals can gently underline. If the vacuum is a state with structure, what else might be encoded in its properties, beyond the masses we've extracted? In the standard model, V sets the electroweak scale, but it also sets the stage for how symmetry hides itself. The vacuum is not just a background, it is part of the dynamical solution. Summarize the construction in the order we used it, because the logic is linear even if the consequences feel surprising. Choose F as in U2 doublet with Y / just 1, 2, so it can couple to both W and B. Write def plus 2, V with V / just 2, plus for 4, and take M2 as 0, so the vacuum sits at non-zero magnitude. The Mexican hat potential then supplies a degenerate family of minima. Then choose phi das as 0, V2 T, using gauge freedom to align the vacuum, and connect V to muon decay through V Gaor to GF 1, 2, 247 GeV. Expand dm of 2 and identify masses, noting that everything comes from a gauge invariant term. Define W plus, W1 IW2, 2, and get MW, G, V2. The charge sector diagonalizes immediately, leaving no ambiguity about the W mass. Diagonalize the neutral sector with θW, defined by tan θW ln dos G, and obtain Zem and Am as orthogonal combinations. Read off MZ bond V2, G2 plus G2, while Am remains massless because Q, T3 plus Y is unbroken. The structure is rigid, and that rigidity is why it becomes a precision framework. It is also why the photon's masslessness is not a tuning, but a symmetry statement. Make the Goldstone disappearance explicit, because it is the conceptual hinge that makes the mechanism work. Parameterize F with 3 Xa fields and 1 H field, and recognize Xa as angular coordinates on the vacuum manifold. Use gauge freedom to remove Xa in unitary gauge, and interpret them as longitudinal polarizations of W and Z, preserving the total degrees of freedom. The mechanism therefore solves 2 problems at once. It gives masses and it removes unwanted massless scalars. End on the remaining mystery that Chapter 6 will need, because the mechanism is not finished until it meets the data. This construction explains how gauge bosons can be massive without breaking gauge invariance, and why the photon remains massless. It also leaves one physical scalar excitation, H, whose couplings and self-interactions must match the particle discovered in 2012. The vacuum has given us a scale, but the experiments will tell us whether the surviving ripple behaves as predicted. Next, we test the mechanism against data. We derive how the Higgs couples to W, Z, and fermions, and why those couplings scale with mass. Then the 125 GeV resonance stops being a coincidence and becomes a measurement of the vacuum itself. In 2012 we found a new particle, but the real discovery wasn't the particle alone. It was evidence that the electroweak vacuum is structured, and that structure fixes which excitations can be massive. For decades, the standard model carried a strange promise. It said the weak force could be unified with electromagnetism, but only if the vacuum itself carried a hidden order parameter, quiet, constant, and everywhere. When the LHC finally saw a resonance at 125 GeV, it was not merely adding a new entry to a particle table. It was revealing that the vacuum behaves like a physical system with measurable stiffness, and that stiffness leaves fingerprints in couplings and decays. Chapter 5 built the loophole. A gauge-invariant Lagrangian expanded around Fourier 0 generates masses without inserting forbidden mass operators. Now the question tightens. What exactly is the Higgs boson in that construction, and what does it mean to measure it? Start with a Higgs doublet after choosing a gauge that exposes physical degrees of freedom. In unitary gauge, the would-be Goldstones are removed from F, and the field is written as a specific representative. The standard model Higgs field becomes EFX, just d 0 vim pulsus HEX 2 dt. This is not a definition by analogy. It is a coordinate choice on field space after using gauge redundancy to eliminate 3 angular modes. Those 3 modes are not deleted in a physical sense. They are absorbed into the longitudinal polarizations of W and Z, which is why those bosons behave as massive spin 1 particles. What remains is the radial fluctuation, the one direction in field space that cannot be gauged away. The remaining real scalar fluctuation h(x) is the physical Higgs boson field. It is a propagating degree of freedom, with its own quantum excitations, and it can be produced as non-shell resonance. In the visual language of the theory, the vacuum sits at a non-zero radius in Higgs field space, and h(x) is the ripple that moves inward and outward from that radius. The vacuum expectation value V is the constant background. It is fixed by low-energy weak data through V walls 2 GF 12246 GeV. That number is not an arbitrary convention, because GF is measured in muon decay with exquisite precision. When you quote V, you are really quoting the strength of charged current weak interactions encoded in the Fermi constant. The Higgs boson is the quantum excitation around that background, not the background itself. That distinction matters because it separates a static property of the vacuum from a dynamical particle you can create and destroy. It also clarifies what the LHC actually did. It did not detect the vacuum. It detected a particular excitation whose existence implies a vacuum structure. To define the Higgs mass, expand the Higgs potential around the vacuum. The potential is V sacra m2 F plus V plul F plus S 2 with m2 0 and L est 0. This sign choice is the entire drama because m-testut 0 makes the origin unstable and forces the field to settle at a non-zero value. In plain terms, the vacuum prefers a non-zero Higgs magnitude. The shape of this potential is often drawn as a Mexican hat surface, but the important physics is the curvature at the minimum. The curvature tells you how much energy it costs to deform the field slightly away from the vacuum value. That energy cost becomes a mass term in the Lagrangian, and the mass becomes the location of a resonance in experiments. Write the expansion in unitary gauge and keep the quadratic piece in h. The result gives mass 2 is 2 of 2 at tree level. This relation is precise in the renormalized theory once L and V are defined at a scale, with loop corrections shifting the simple picture. Those corrections are not cosmetic, because the Higgs is a scalar, and scalars are unusually sensitive to quantum fluctuations. This is the first meaning of mass in the Higgs story. Mass is the coefficient of the quadratic term in the Lagrangian for small oscillations around the vacuum. In quantum field theory, it is the pole of the propagator, and experimentally it is the resonance position. When Atlas and CMS quote a Higgs mass, they are reconstructing the pole location from decay products, then mapping it back onto the parameters of the theory. But even this definition hides a subtlety. A particle's observed line shape reflects both its intrinsic width and the detector resolution, and at the LHC the Higgs is far narrower than the detectors can directly resolve, so the mass is extracted from sharp channels like GG and ZZ4L, where the energy measurement is clean enough to locate the peak. Now the central structural claim becomes testable. If the vacuum value V generates W and Z masses through DEM port 2, then the same term fixes how H couples to W and Z. The Higgs boson is not an optional extra field. It is the fluctuation that must appear if the vacuum value is dynamical, rather than imposed by hand. Take the gauge boson mass terms from chapter 5 and do one more step. Replace Vc by V plus Hx inside the same gauge invariant operator that produced the masses. The quadratic terms in gauge fields give masses, and the linear terms in H give interactions. This is the key visual move. One operator expanded once more, revealing both mass and coupling as two faces of the same structure. For the charge sector, the W mass term is MW2 W slalem W san mem, with MW GV2. Promoting V dV plus H produces trilinear interaction. The leading coupling is 2W2V H dupl sem W kiram. That coefficient is not a guess, and it is not tuned to match data. It follows from gauge invariance and the normalization of the Higgs field, once V is fixed by GF. In a collider event display, this coupling is the reason a Higgs can be radiated off a W line, and it is also the reason vector boson fusion exists. For the neutral sector, the Z mass term is 1.2 as S Z2 Z SM Z with MZ just V2 G2 plus G2. The same replacement generates MZ2V HZ just. These are not guessed vertices. They are enforced by the same V that appears in the mass terms, because both come from stem mod 2. That is why the phrase coupling proportional to mass is not a slogan. It is a consequence of expanding a single gauge invariant structure. This proportionality has a sharp meaning. The Higgs coupling to W and Z is fixed once V and the gauge structure are fixed. There is no free parameter that can change GHW and GAHZ independently while keeping the minimal standard model intact. If experiments ever saw a mismatch in that pattern, it would point to additional fields, mixing, or higher dimension operators. The same logic applies to quartic couplings. Expanding V plus H2 produces H2WW, and are Toulson Z terms with coefficients also fixed by MW, MZ, and V. Those higher couplings matter in loop processes and in unitarity cancellations at high energy. They also matter conceptually, because they show the Higgs is woven into the theory's consistency, not merely appended to it. There is a historical shadow here. Before the Higgs was discovered, the standard model still made predictions about high-energy WL-WL scattering, where the longitudinal modes dominate. Without a Higgs-like contribution, the scattering amplitudes would grow with energy and violate unitarity at the TV scale. The Higgs is not just a mass generator, it is part of the mechanism that keeps the theory predictive at high energies. Now turn to fermions, where the story is both similar and more mysterious. Gauge invariance forbids a bare Dirac mass term because left and right chiralities transform differently. The left-handed fermions sit in SU2 doublets, while the right-handed ones are singlets, so a direct mass term would not respect the symmetry. The standard model allows masses only through Yukawa interactions that include F. Write the Yukawa term for a fermion F schematically as Ly. Nouns your Y FFL FFR plus HC. For uptype quarks, the Higgs appears as the conjugate doublet, but the structure is the same. The Yukawa coupling YF is dimensionless and gauge invariant because F carries the missing quantum numbers. In effect, F acts as the bridge that lets left and right talk to each other without breaking the gauge rules. Insert the unitary gauge form Bex as Mex 0 Vos plus H 2 T. The Yukawa term becomes a mass term plus an interaction term. The fermion mass is MF. Gra F Vos 2. The Higgs fermion coupling is then fixed in terms of that mass. The interaction contains MF HFF. So within the standard model, once a fermion's mass is known, its Higgs coupling is predicted. This is another precise meaning of coupling proportional to mass, now applied to matter fields. Yet the deeper point is what is not predicted. The Yukawa couplings were for free parameters of the standard model. The theory does not explain why YE is tiny, why YT is near 1, or why the pattern spans orders of magnitude. Even the question of why the Yukawa matrices have their particular flavor structure remains unanswered within the minimal framework. So the Higgs mechanism explains how fermions can have mass without breaking gauge invariance. It does not explain why those masses take their observed values. The vacuum supplies the scale V, but the Yukawas decide the hierarchy. When you look at the fermion spectrum from the electron to the top quark, you are looking at a set of numbers the standard model simply accepts. This is where the word mass gains a second layer of meaning. For W and Z, mass is tied to gauge symmetry and V. For fermions, mass is tied to V and unknown Yukawa numbers. The vacuum is universal, but the coupling strengths are not. That contrast is one of the reasons the Higgs discovery felt like both an ending and a beginning. Now define the Higgs boson operationally in collider physics terms. The Higgs is the quantum field H or X, whose interactions are fixed by the standard model Lagrangian. Experiments do not observe HIX directly. They infer it from production and decay rates consistent with those interactions. In the control rooms at CERN, the Higgs is not a field, and it is not a potential. It is a pattern in the data, a set of excesses, correlated across channels, each with its own backgrounds and systematics. The identification comes from coherence. One mass, one set of couplings, many different experimental signatures. At the LHC, Higgs production is not a single process. It is a set of channels with different initial states, different kinematics, and different theoretical uncertainties. The pattern across channels is part of the identification. A real Higgs-like state must appear consistently, whether it is produced with jets, with vector bosons, or alongside top quarks. The dominant production mode at 13 TeV is gluon fusion. Two gluons couple to the Higgs through a heavy quark loop, dominated by the top Yukawa coupling. This is already a crucial point. Even when the Higgs is produced from gluons, the top quark is effectively in the amplitude. In a sense, the LHC produces Higgs bosons by briefly borrowing the influence of the heaviest fermion. Gluon fusion also illustrates how quantum field theory works in practice. The Higgs does not couple directly to massless gluons at tree level, because it is color neutral. The coupling is induced by loops, and loops are sensitive to any heavy colored particle that can circulate. That is why precision measurements of gluon fusion are also indirect searches for new physics. The next major mode is vector boson fusion. Two quarks radiate W or Z bosons that fuse into a Higgs, leaving forward jets and a distinctive topology. This channel is directly sensitive to the HWW and HZZ couplings. Visually, it looks like two energetic sprays of hadrons, separated by a wide rapidity gap, with the Higgs decay products appearing in the quiet central region. Associated production provides additional handles. In VH production, a Higgs is produced with a W or Z, giving leptons that tag the event and help isolate H, BB. In TTH production, a Higgs is produced with a top pair, directly probing the top Yukawa in a way gluon fusion alone cannot fully isolate. These channels are rarer, but their clean tags turn them into precision tools. There are also rarer modes like TH and B-associated production, which become important when testing sign choices and small couplings. Each mode is a different projection of the same underlying couplings. The standard model predicts their relative sizes once the couplings are fixed. When experiments compare these rates, they are checking whether one set of parameters can explain them all. Now turn to decays, because decays are where the Higgs becomes visible. A Higgs at 125 GeV is not heavy enough to decay to two on-shell W bosons or two on-shell Z bosons simultaneously. That kinematic fact shapes the entire observed decay pattern. It forces the Higgs to live in a world of off-shell vector bosons, loops, and competing fermionic channels. The largest branching fraction is H, BB. It is the most common decay, but it is experimentally difficult because QCD backgrounds are enormous. In the detector, B-jets are everywhere, produced by mundane strong interactions at rates that dwarf the Higgs signal. The signal is extracted using associated production and sophisticated multivariate methods, where the presence of a W or Z acts like a beacon. The next large branching fraction is H, WW. 1W is off-shell at 125 GeV, but the rate is still substantial. The final states include leptons and missing energy, which are cleaner than jets but less reconstructible due to neutrinos. The event looks like a partial story. Visible leptons tracing arcs in the tracker, and invisible momentum inferred from the imbalance. The decay, H, is rarer but extremely clean in the 4-lepton final state. 1Z is off-shell, yet the invariant mass reconstruction is precise. This channel is central to measuring the Higgs mass and testing spin and parity through angular correlations. In the most iconic events, 4 isolated leptons emerge like a geometric signature, almost background-free. The decay HTT probes the Yukawa coupling to leptons directly. It is challenging due to neutrinos in T decays, but is essential for establishing that the Higgs couples to fermions as predicted. Reconstructing T-pairs requires careful accounting of missing energy and collimated decay products, and the analysis becomes a test of both theory and detector performance. The decay, HGG, is rare, but it is a discovery channel because it produces a sharp mass peak. It occurs through loops, primarily W loops and top loops, which interfere. That interference makes GG sensitive not just to magnitudes but to relative signs of couplings. In a single spectrum, a small bump becomes meaningful because it sits on a smooth background with high resolution. Other loop-induced decays like HEA, Z are even rarer and remain precision targets. Invisible or exotic decays would signal physics beyond the standard model. The absence of large exotic branching fractions is itself a constraint. Each missing decay is a silence that still carries information. Branching ratios are not arbitrary. They are computed from partial widths, GZI, and the total width, GI tot. Each partial width depends on the relevant coupling squared, phase space, and loop factors when applicable. Measuring branching fractions is therefore a way of measuring couplings, but only after accounting for the total width. At 125 GeV, the Higgs total width in the standard model is only a few MeV. That is far below the detector mass resolution, so the width cannot be measured directly from the resonance shape at the LHC. Instead, experiments constrain the width indirectly through off-shell production and global coupling fits. The logic is subtle, using rates at higher invariant masses to bound how strongly the Higgs can couple, even when it is not produced on its mass shell. Now state what CERN actually measured in 2012 in the language that connects to the theory. ATLAS and CMS measured excess event rates in specific final states, consistent with a new resonance near 125 GeV. They combined channels like GRG and ZZ4L with others that had weaker resolution. The discovery was not one dramatic spike in one plot, but a convergence of evidence across independent analyses. The discovery established several core properties quickly. The new particle was narrow compared to detector resolution, consistent with a weakly coupled scalar. It decayed to 2 photons, which immediately constrained spin, because a simple on-shell spin 1 state cannot decay to G. That single fact, 2 photons from a new resonance, already carved away a large space of possibilities. Spin and parity were tested more directly through angular distributions in H, Z-Z's, 4L, and through production kinematics. The data favoured JP, Stasplines, and disfavoured many alternative hypotheses. This was not philosophical. It was a statistical comparison of differential distributions to predicted templates. The angles between leptons, the invariant masses of intermediate states, and the event shapes became a kind of forensic reconstruction. But identifying preauxes was not yet the full Higgs mechanism. A scalar could exist without being the standard model Higgs. And extended Higgs sectors can produce a 0+ state with modified couplings. So the next step was to test whether its couplings match the pattern enforced by V. The question became sharper. Is this scalar the vacuum's radial mode or merely a lookalike? This is where the concept of signal strength enters. Experiments report M, defined as the observed rate in a channel, divided by the standard model prediction. Rate means S, pph, x, br, hx, for a given production and decay selection. The definition is simple, but the extraction is intricate, because each channel has its own backgrounds and efficiencies. So M1 means the observed yield matches the standard model expectation within uncertainties. It does not mean every coupling is exactly standard model. It means the product of production and decay probabilities is consistent with the standard model across the measured channels. A deviation could hide in correlated shifts or in unmeasured decay modes that change the total width. Global fits translate the set of measured M values into constraints on coupling modifiers key. One writes GHVV says to KVG SFVV SM and GHF KSFG SM, then fits K parameters to data. In the standard model, key values are 1. The power of this approach is that it compresses many measurements into a map of how Higgs-like the particle truly is. These fits are not unique without assumptions. If there are invisible decays, the total width increases and all visible branching fractions decrease, which can mimic coupling changes. If there are new loop particles, GG and GG couplings can shift without changing tree-level couplings. So coupling extraction is a map from data to theory space, not a single number. Still, the broad result is striking. Across gluon fusion, VBF, VH, and TTH, and across GG, ZZAD, WWW BB, and TT, the pattern is consistent with a single scalar whose couplings track standard model expectations. The data are not perfect, but the coherence across channels is the key. It is the experimental shadow of the theoretical structure. That coherence carries a quiet implication. The same V that gives W and Z their masses predicts the HWW and HZZ couplings. The same Yukawa terms that give fermions their masses predict Kirchhoff couplings proportional to MMF. The LHC is testing whether the vacuum structure inferred from weak interactions is the same structure behind the 125 GeV resonance. Now clarify a common misunderstanding without using analogy. The Higgs boson does not give mass as an active agent pushing on particles. The Higgs field's vacuum value changes the form of the quadratic terms in the Lagrangian, and those terms define masses. The mechanism is mathematical and structural, not mechanical. Particles do not become heavy because they are slowed down by a medium. They are heavy because the spectrum of excitations around the vacuum includes massive poles. Mass is a property of the propagator and the representation content after symmetry breaking. When you change the vacuum, you change which fields mix, which combinations propagate, and which poles appear. In that sense, the Higgs boson is not the cause of mass in general. It is evidence that the vacuum has a non-zero scalar order parameter, and that this order parameter appears in gauge invariant operators that connect to W, Z, and fermions. It is a measurement of the vacuum's organization, made visible as a particle. Also separate two uses of the word Higgs. The Higgs field F is the SU2 doublet with a vacuum value V. The Higgs boson is the quantum excitation Hx around that vacuum after gauge fixing. Confusing those two makes the story sound mystical, because it hides the difference between background and particle. The theory becomes clearer when that distinction is kept explicit. Now, push the narrative toward the climax. If the Higgs boson is the fluctuation of the vacuum magnitude, then measuring its couplings is a way of measuring the vacuum itself. Every deviation in a coupling is a clue about whether the vacuum is minimal or part of a larger structure. Even a few % shift would be a message from physics beyond the standard model. This is why the Higgs is a portal to unknown physics even when it looks ordinary. A scalar can mix with other scalars. A doublet can be part of a multi-doublet sector. The Higgs can couple to hidden states that do not carry standard model charges, changing its width and branching fractions. The LHC's task is to look for tiny inconsistencies in an otherwise consistent pattern. Precision matters because the standard model is rigid. The relations among couplings are not independent. If key V differs from 1, unitarity in longitudinal vector boson scattering demands additional new physics at some scale. If key F differs, flavor constraints and loop observables shift. The Higgs sits at the intersection of collider data, electroweak precision tests, and quantum consistency. The Higgs self-coupling is another frontier. The potential parameter L sets both MH and the H3 and H4 interactions in the minimal model. Measuring double Higgs production probes L, but current uncertainties are large. This is a direct test of whether the Higgs potential we wrote is the whole story, or merely the first approximation. Now address what the Higgs does not explain, because the mystery deepens here rather than resolves. The standard model contains M2 and L as parameters in VF, and it contains Yukawa couplings YF as parameters in LY. The mechanism relates these parameters to masses, but it does not predict their values. It tells us how the machine works, but not why its dials are set as they are. First, the origin of the Higgs potential parameters is unknown. Why is M2 negative, and why is V at 246 GeV rather than at some much larger scale? In the standard model, these are inputs, not outputs. The theory accepts the electroweak scale and builds a consistent world around it. Second, the hierarchy problem is a structural tension. Quantum corrections to the Higgs mass parameter are sensitive to high scales, so keeping V far below a cutoff requires either symmetry protection, dynamics, or tuning. The standard model works as an effective theory, but it does not explain why the electroweak scale is stable. This is not a complaint about beauty, but a statement about how renormalization treats scalars. Fermion masses are protected by chiral symmetry, and gauge boson masses are protected by gauge symmetry, but a fundamental scalar has no comparable protection in the minimal model. That is why the Higgs feels exposed. Its mass parameter is a place where unknown ultraviolet physics can leave large imprints, unless something cancels or forbids them. Third, the Higgs does not explain dark matter. The standard model has no stable neutral particle with the right abundance and interactions. The Higgs could couple to a hidden sector, but that is an extension, not a consequence. The very fact that the Higgs is a scalar makes it a plausible mediator, yet the minimal theory remains silent. Fourth, the Higgs does not explain neutrino masses in the minimal standard model. Without right-handed neutrinos or higher dimension operators, neutrinos remain massless. The observed neutrino masses imply additional structure, which may or may not connect to the Higgs sector. The vacuum we have measured may be only part of the story that shaped the lepton sector. Fifth, vacuum stability is an open question that makes the tone of the story darker. The Higgs quartic coupling runs with energy scale under renormalization group flow. The top Yukawa tends to drive L downward at high scales. The same heavy top quark that dominates gluon fusion also influences the fate of the potential at enormous energies. With current measured values of MH and MT, the standard model vacuum appears near the boundary between absolute stability and metastability. That means the electroweak vacuum might not be the deepest minimum of the potential when extrapolated to very high energies. It could be long-lived but not fundamental. The vacuum would then be a durable state, yet not the final one. This is not a prediction of imminent decay. It is a statement about extrapolation and about the sensitivity to precise inputs, yet it reframes the vacuum as a contingent state, not an inevitable one. If the vacuum is metastable, then the universe is sitting in a valley that is not the lowest possible valley. So the Higgs boson is both a confirmation and a question mark. It confirms that the electroweak vacuum has a scalar order parameter with V246 GeV. It confirms that a physical scalar excitation exists with MMH125 GeV and couplings broadly consistent with the standard model. It confirms that the loophole built by gauge invariance is how nature actually works, but it also exposes the emptiness of our explanation for the numbers. We do not know why the Yukawas take their values. We do not know why M2 is what it is. We do not know whether the Higgs is alone or the visible part of a larger vacuum sector. The discovery answered the question of existence, while sharpening the question of origin. Now connect back to the central question in its most precise form. What is the Higgs boson? It is the scalar field Hx appearing in Fx, and 0, VV plus Hx, 2 and after gauge choice, with mass m hastus 1 to 11 warprost, and with couplings fixed by expanding gauge invariant operators around V. How does the background Higgs field generate particle masses without breaking gauge symmetry? It does so because the Lagrangian remains gauge invariant, while the vacuum chooses a non-zero value that reorganizes the spectrum. Mass terms and Higgs couplings arise together from the same gauge invariant structures. The symmetry is not destroyed in the equations, but it is hidden in the state. Now the chapter's final beat should keep the tone mysterious. The Higgs looks like a particle, but it is also a measurement of a vacuum state. The vacuum is not a blank stage. It is a dynamical configuration with parameters we do not understand. When the detectors see a Higgs decay, they are seeing a brief localized disturbance of that configuration. The LHC has measured that this vacuum has a ripple at 125 GeV, and that the ripple talks to W, Z, and fermions in the pattern the standard model demands. Yet the deeper question remains: why this vacuum? Why this scale? And why these couplings? The numbers fit together, but they do not yet explain themselves. Next chapter we step back from the couplings and ask what the Higgs implies about the universe's history. We ask whether the vacuum changed in the early universe, and whether the Higgs sector hides additional fields, phases, or symmetries still unseen. We began with a 2012 particle, then followed the deeper claim that vacuum is structured. Chapter by chapter we made that claim precise, in Lagrangians, symmetries, and measured couplings. Now we take the same Higgs field into the early universe, where temperature reshapes what vacuum even means. Cosmology forces a sharper definition of vacuum than everyday language allows, because empty can still be full of energy and excitations. In quantum field theory, vacuum is the lowest free energy state consistent with the conditions we impose. In the early universe, those conditions include a hot, dense plasma, so the relevant object is not the zero temperature potential, Vf. It is the finite temperature effective potential V(CSF)Ft, the free energy density for a coarse-grained Higgs background. Visually, this is where the story changes scale. We move from a quiet collider event display to a universe filled edge to edge with radiation. Imagine a fog of particles so energetic that collisions happen faster than any laboratory clock. In that environment, vacuum is not the absence of particles. It is the preferred background field value inside a thermal bath. V sum F, Ft is not a new theory. It is the same standard model reorganized around a different statistical state. Instead of computing amplitudes in empty space, we sum over fluctuations in a heat bath. Quantum fluctuations still contribute, but thermal excitations add their own corrections, and those corrections have a clear physical meaning. The Higgs background becomes an order parameter whose preferred value can change with temperature, much like a magnet's alignment changes with heat. Except here the alignment is a field value. The question becomes operational and testable in principle, even if the universe is the only laboratory. What value of Fermi minimizes Vf at a given t, and how quickly does it move as the plasma cools? In practice, we compute Vf using finite temperature field theory, where bosons and fermions contribute differently. Bosonic modes enhance infrared effects and can reshape the potential more dramatically, while fermions tend to smooth certain features. The details matter because the electroweak transition is a competition between these contributions. At zero temperature, we expand around phasis v2, and masses follow from that choice. For W and Z, masses come from μ2 evaluated on the vacuum. For fermions, masses come from Yukawa terms after inserting the same vacuum value. In the language of Chapter 6, the Higgs boson is the fluctuation Hx around that vacuum magnitude. It is worth lingering on what expand around really means, because it is easy to treat it as a trick. We choose a background field configuration that minimizes the energy, then describe small ripples on top of it. Those ripples propagate as particles, and their interaction strengths are fixed by the same couplings that appear in the Lagrangian. The vacuum value is not an extra ingredient added by hand, it is the field's preferred state once the potential is specified. At high temperature, thermal corrections favour the symmetric point φ0. In simple terms, the plasma populates excitations that add positive curvature near the origin, making f0 energetically attractive. The effective mass parameter becomes m2t, m2 plus ct, with c set by gauge couplings, Yukawa couplings, and the Higgs self-coupling. When t is large enough, m2t becomes positive, and the minimum shifts to f0. A useful visual here is a sequence of curves. At low temperature, the familiar Mexican hat shape has a ring of minima away from the origin. As temperature rises, the hat slowly fills in, until the lowest point slides back to the centre. Nothing mystical happens to the equations. The free energy landscape changes because the medium changes what fluctuations are available. This is symmetry restoration in explicit field theory terms. The electroweak gauge symmetry is not broken by the vacuum when the minimum is at f0. The unbroken phase is not a different set of rules, it is the same Lagrangian with a different preferred background. The spectrum reorganizes again, just as it did when we first expanded around φ0. Historically, the idea that symmetries can be restored at high temperature became central in the 1970s, when particle physics and early universe cosmology began to merge into a single narrative. The Higgs mechanism had explained how masses could arise without destroying gauge invariance. Cosmology then asked a sharper question. If the vacuum can choose a symmetry-breaking configuration today, what did it choose when the universe was hotter? Finite temperature methods provided the answer in a calculable way. Now place that in the cosmic timeline with numbers that anchor the story. The electroweak epoch corresponds to temperatures around 100 GeV. That is roughly 10^12 seconds after the Big Bang, when the universe was a dense relativistic plasma. In that plasma, typical particle energies are of order T, so masses matter only if m is comparable to T. The visuals can be almost abstract, because the universe is still too young for atoms or light. Picture a horizon-sized region as a seething, nearly uniform glow with tiny statistical fluctuations riding on top. Quarks, leptons, gauge bosons, and Higgs excitations scatter constantly, and the mean free paths are microscopic. Expansion is real, but local thermal equilibrium is still an excellent approximation for many processes. In the restored phase, the Higgs vacuum expectation value is effectively zero. Then the tree-level masses mw, gv2, and mz G2 vanish because Vt vanishes. Fermion masses μmf and fv2 vanish for the same reason. Operationally, W, Z, quarks, and leptons behave as effectively massless species in the plasma, aside from thermal masses from interactions. That effectively is important, because the plasma does not let particles behave as if they are in empty space. Interactions with the medium dress the propagators and shift dispersion relations, so energy and momentum no longer satisfy the simple vacuum relation E2, P2 plus SM2. Instead, there are collective excitations, screening effects, and modified poles. The language is technical, but the plain meaning is simple. The medium changes how particles move. Those thermal masses are not the same as Higgs masses, and they do not break gauge symmetry. They arise from propagation in a medium and modified dispersion relations. They do not correspond to a vacuum pole mass measured in empty space. This distinction matters because it keeps the narrative honest. The Higgs mechanism is about the vacuum background, not about drag or friction. As the universe expands, it cools, and Vt changes shape. At some temperature, the minimum moves away from φ0, and the Higgs field acquires a non-zero expectation value again. This is the electroweak phase transition in broad terms. It is not a single event everywhere at once. but a change in the preferred order parameter as conditions evolve. To visualize that change, imagine the universe as a gradually dimming furnace. The free energy surface for F is like a landscape, whose valleys shift as the temperature drops. The Higgs field does not decide in a human sense, but it does relax toward the lowest free energy configuration available. The pace of that relaxation depends on interaction rates, expansion, and whether barriers appear. The nature of that transition depends on the detailed shape of VF. A first-order transition occurs when VF develops two separated minima with a barrier between them. Then the system can supercool and transition by nucleating bubbles of the broken phase. A smooth crossover occurs when the minimum shifts continuously without a barrier, so there is no latent heat and no bubble nucleation. To say this without analogy, focus on the order parameter and the free energy landscape. In a first-order case, there is a range of T where F mass of 0 is locally stable, while F0 is also locally stable. The barrier makes the transition out of equilibrium because the system must tunnel, or thermally hop. In a crossover, equilibrium is maintained more closely as the minimum drifts. In field theory language, the barrier is often associated with cubic terms generated by bosonic thermal loops, which can create a bump between the symmetric and broken configurations. Whether that bump is large enough depends on the Higgs mass and the couplings that control the thermal corrections. This is why the problem became quantitative once the Higgs mass was measured. The mass fixes L, and L helps determine the shape of VEF at finite temperature. Now connect this to the cosmic asymmetry that motivated much of particle cosmology. The universe contains far more baryons than antibaryons, quantified by a small baryon to photon ratio. If matter and antimatter had been produced in perfect symmetry, they would have annihilated almost completely, leaving a universe of radiation. The fact that we exist is evidence that something biased the outcome. Any explanation must satisfy Sakharov's conditions. It must violate baryon number, violate C and CP, and occur out of thermal equilibrium. These are not philosophical requirements. They are bookkeeping constraints built into quantum statistical mechanics. If you keep equilibrium, detailed balance tends to erase any net asymmetry. If you keep CP symmetry, processes create matter and antimatter at equal rates. The standard model satisfies the first condition in a subtle way. Non-perturbative electroweak processes violate B+L through the chiral anomaly, via Sphaleron transitions at high temperature. This is not a failure of gauge symmetry. It is a quantum effect in the global currents. It is the earlier anomaly thread returning in a cosmological setting. A Sphaleron is best thought of as a saddle point in the energy landscape of the electroweak gauge and Higgs fields. At zero temperature, tunneling between topologically distinct vacua is exponentially suppressed. At high temperature, the plasma can climb over the barrier instead of tunneling through it, and transitions become frequent. Each transition changes baryon and lepton number together, while conserving BL. The standard model also violates CP, but not enough for the observed asymmetry in typical estimates. CP violation comes from the CKM phase in the quark sector. In the hot plasma, its effects on baryogenesis are strongly suppressed by small Yukawas and flavor structure. The suppression is not merely numerical, it is structural, because the relevant CP-odd combinations involve multiple generations and small mass differences. The third condition, departure from equilibrium, depends critically on the electroweak transition being strongly first order. If expanding bubbles create moving phase boundaries, then particles scattering off those boundaries can experience CP violating effects that bias baryon number production. If the transition is a crossover, the universe remains too close to equilibrium for this mechanism to work efficiently. The Higgs potential is therefore not just a detail, it is the stage on which the asymmetry must be produced. Now the key point that closes a loophole many viewers may hope for. With a Higgs mass near 125 GeV, the standard model predicts the electroweak transition is not strongly first order. Lattice studies and perturbative analyses indicate a crossover for the physical parameters. That means no robust bubble nucleation and no strong out-of-equilibrium dynamics at the electroweak scale. The lattice result is especially important because the transition involves infrared gauge dynamics that are hard to capture reliably in simple perturbation theory. Numerical simulations of the dimensionally reduced effective theory show that, for the observed Higgs mass, the would-be barrier is washed away. The order parameter changes smoothly, and the system does not release latent heat in a sharp event. Cosmology, in other words, reads the Higgs mass as a statement about the universe's thermal history. This is why standard model electroweak baryogenesis is essentially ruled out. Sphalerons remain active through the crossover and tend to wash out any baryon asymmetry produced earlier, unless it is protected by BL. The CKMCP violation is too small to generate enough asymmetry in the first place. The Higgs we measured therefore constrains not only collider physics, but cosmic history. There is a sobering clarity to this. The same data that confirm the Higgs mechanism also limit one of the most elegant cosmological ideas tied to it. The standard model works remarkably well, yet it seems to leave the origin of matter unfinished. That gap is not a failure of imagination, it is a quantitative mismatch between what the model can produce and what the sky contains. Now widen the frame without overselling. If the Higgs sector is extended beyond the standard model, VF can change dramatically. Additional scalars can strengthen the transition and create a barrier. New CP violating phases can appear in scalar interactions or Yukawa-like couplings. In such models, electroweak baryogenesis can become viable again. The visual language here often shifts to what-if diagrams. A second Higgs doublet, a singlet scalar, or other minimal additions can alter thermal loop effects and introduce new terms in the effective potential. The key is not exotic complexity, it is targeted change, enough to create a barrier and enough CP violation to bias the plasma. The Higgs field becomes a portal because it couples to so much of the standard model. A first-order electroweak transition would also have another consequence. Bubble nucleation and collisions, plus plasma turbulence and sound waves, can source a stochastic gravitational wave background. The peak frequency today would fall in the millihertz range for an electroweak scale transition, depending on details. This is why space-based detectors like LISA are often discussed in the same breath as Higgs cosmology. To picture this, imagine bubbles of the broken phase expanding at relativistic speeds, their walls sweeping through the plasma. Collisions do not just rearrange fields, they stir the medium, creating long-lived acoustic waves and vortical motion. Those bulk motions carry quadrupole stress, and in general relativity that means gravitational radiation. The signal would be faint, but it would be a fossil of a time when the vacuum itself was changing. The logic is conditional, and should stay that way. Gravitational waves are not a guaranteed Higgs signal, and the standard model alone predicts no strong first-order transition. But the Higgs field is the portal through which many extensions imprint themselves. A gravitational wave detection with the right spectrum would be evidence for new vacuum dynamics, not merely for the Higgs Boson's existence. Now return to the Higgs potential itself, because cosmology forces us to ask about its behaviour far beyond 125 GeV. The Higgs quartic coupling L is not a constant, it runs with energy scale under renormalization group flow. The top Yukawa coupling drives L downward at high scales. Gauge couplings push in the opposite direction, but for measured values the downward pull is significant. Running is the price of quantum field theory's consistency across scales. When we probe shorter distances, we effectively change the resolution at which we describe interactions. Virtual particles in loops contribute logarithmic corrections, and those corrections can be absorbed into scale-dependent couplings. The renormalization group then becomes a map from laboratory measurements to extrapolations about the far ultraviolet. Extrapolating the standard model to very high energies suggests L may become negative at around 10.9 to 10.12 GeV, with sizable uncertainty. If L turns negative, the effective potential at large field values can develop a deeper minimum than the electroweak one. Then our vacuum is not absolutely stable. It is metastable, meaning it is a long-lived local minimum separated by a barrier. A good visual is a potential that looks safe near the origin, then subtly bends downward at enormous field values. The electroweak minimum remains where we live, but far away there may be a lower valley. The distance in field space is so large that ordinary intuition fails. Still, the mathematics is straightforward. The sign of L at high scale controls the curvature of the potential at large f. Metastable does not mean fragile on human timescales. The decay rate is computed from quantum tunneling, roughly exp SE, with a large Euclidean action for the bounce solution. For the central values of MEH and MT, the inferred lifetime is vastly longer than the age of the universe. The uncertainty is dominated by the top mass and by theoretical matching between measured parameters and running couplings. It also matters that decay, here, does not mean a slow leak. If a bubble of the true vacuum nucleated, it would expand at near light speed, converting space to a different phase. That is the dramatic image people remember, but the calculated probability is extraordinarily small under standard model assumptions. The responsible statement is not fear, but conditional inference. Stability is a question about extrapolation. This is another place to avoid sensationalism while keeping the mystery. Metastability is a statement about extrapolation, and about the standard model treated as valid to extremely high scales. New physics could alter the running and stabilize the potential, or it could destabilize it further. The Higgs is again the handle, because L is the parameter that defines the vacuum's stiffness. Cosmology adds a further twist, because the early universe explored high energies and large fluctuations. During inflation or reheating, if those occurred at high scales, Higgs field fluctuations could have been large. Whether that threatens vacuum survival depends on the inflationary Hubble scale, couplings to curvature, and unknown ultraviolet physics. The standard model alone cannot give a final answer, but it frames the question sharply. Here the visuals can return to the largest possible canvas. Inflation, if it happened, stretches quantum fluctuations to cosmic size, turning microscopic randomness into macroscopic structure. If the Higgs field participates even weakly, its fluctuations could sample regions of the potential far from today's minimum. Did the universe have to avoid dangerous field values, or was it naturally safe because of additional couplings we have not measured? Now tie these threads back to the central question of the series. What is the Higgs boson precisely without analogy? It is the quantized excitation, G or X, of the Higgs field's radial mode around a vacuum configuration. That vacuum configuration is a non-zero expectation value of an SU2 L doublet, which reorganizes the electroweak theory while keeping gauge invariance intact. The boson is the ripple, and the vacuum value is the background that sets masses. Cosmology forces us to add one sentence to that definition. The Higgs vacuum is not fixed once and for all, it depends on the state of the universe. At high temperature, the effective potential restores symmetry and drives F towards zero. As the universe cools, F becomes non-zero and the familiar masses emerge. Mass is therefore not only a property of particles, it is a property of which vacuum the universe occupies. That observation can be unsettling if we are used to thinking of mass as intrinsic. In the standard model, mass is relational because it is set by couplings to a background field. Change the background and the spectrum reorganizes, even though the underlying gauge structure remains. The early universe is the proof that this is not a metaphor. It is a phase of reality the cosmos actually passed through. Now bring the story to its final synthesis, with the tone held steady. The Higgs field is our most direct probe of vacuum structure, because it has a measurable excitation and a measurable vacuum value. We measured V through weak processes long before we saw H at the LHC. We then measured H and found couplings consistent with that same V, linking collider events to the ground state of the theory. Yet the Higgs also marks the boundary of our understanding. The standard model does not explain why M2 is negative, why V is 246 GeV, or why Yukawa coupling spans so many orders of magnitude. It does not explain whether the electroweak transition was a crossover by necessity, or merely by the minimal field content we have seen. It does not explain whether our vacuum is unique, selected, or accidental. The deeper mystery is not a poetic add-on. It is a physical statement about what vacuum means. Vacuum is a state with energy, with correlations, and with symmetry properties that can change with conditions. The Higgs is the simplest field that makes that statement experimentally concrete. It proves that empty space is not nothing, and it hints that empty space has a history. So the final answer is also a reframing. The Higgs boson is not a mystical source of mass. It is a measurable excitation of a scalar field. The field's vacuum value sets the mass scale of known particles by reorganizing the electroweak theory without breaking its gauge symmetry. And the cosmos reminds us that this vacuum was once different, and could have been different again. We end where we began, with the real discovery behind the particle. In 2012, we found a new resonance, but we also confirmed that the vacuum is a physical entity. The Higgs gives us a handle on its structure, its temperature dependence, and possibly its ultimate stability. It still leaves the most unsettling question untouched. Why this vacuum, and what other vacua are hidden in the mathematics of empty space? We began with a bump in the data, a narrow resonance at 125 G, and ended with a statement about the vacuum itself. The real discovery was not a mass particle, but a consistent electroweak theory where fields, symmetries, and the action determine what terms are even allowed. A scalar doublet with a non-zero vacuum value reorganizes the spectrum, gives W and Z their masses through just 2, leaves the photon exactly massless, and turns the remaining radial fluctuation into the Higgs boson we can actually produce and measure. Along the way, the mathematics forced a particular kind of honesty about what mass means in quantum field theory. It is a pole in a propagator, a curvature of a potential around the vacuum, and a parameter that can be extracted from line shapes and branching fractions. The same operators that generate the W and Z masses also fix the Higgs couplings to them, so the 2012 signal was immediately a test of structure, not just existence. And when we move from collider time to cosmic time, the Higgs vacuum stopped being a static backdrop and became an evolving order parameter, restored at high temperature, and only later settling into the value that now quietly calibrates the electroweak world. That arc also resolved the apparent contradiction we planted early, the one that global symmetry breaking seems to demand massless Goldstone particles. In a local symmetry, those Goldstone directions do not survive as extra-physical scalars. They are rebooked into the gauge fields as longitudinal polarizations, preserving gauge invariance while changing what counts as a particle. The price of that consistency is subtlety. Because gauge symmetry is not broken in the Lagrangian, it is hidden in the vacuum and in how we choose variables. Even the parts we only touched, anomalies and radiative corrections, underline the same theme. Quantization can either respect a symmetry or sabotage it, and loops quietly shift the tree-level relations we write so confidently, turning precision measurements into a microscope for new physics. Finally, the Higgs field is not only an explanation for masses, it is a new kind of cosmic ingredient. Its finite temperature potential tells us that masses can effectively vanish in the early universe without the theory losing gauge consistency. And its zero temperature potential hints at deeper puzzles, from metastability to naturalness to whatever sets the electroweak scale at all. The Higgs boson, in that sense, is a messenger from a structured vacuum whose parameters we can measure, but whose origin we still do not understand. So what is the Higgs boson, mathematically and physically, and how can a background field give mass without breaking gauge symmetry? It is the quantized excitation Hx around a non-zero vacuum value, F, scan 0, V2T, and that vacuum makes gauge invariant terms behave like mass terms after we expand the theory about the chosen ground state, with the would-be Goldstones absorbed into W and Z while U1m remains unbroken. In 2012, we proved that empty space is not a void. It is a specific state of a quantum field, and its value is written into every weak interaction. The lingering mystery is not whether the Higgs exists, but why this vacuum exists, why it has this scale and what else it is still hiding, quietly, everywhere, all at once. If you want to follow the next layer of the story, watch how precision loops, anomalies, and vacuum stability turn a discovered particle into an ongoing interrogation of the standard model.